Hi everyone! In this course we'll be studying graph theory. A graph is a simple yet incredibly useful concept which has found many applications in virtually every branch of math and computer science. We use graph applications daily. Just to name a few: cell phone network, GPS navigation, internet search queries. In order to understand the concept of a graph, let us start with the following problem. There is a small country with 5 cities which we call A, B, C, D and E. And there are 6 round flights between them. You can fly from A to B or from B to A. You can fly between A and C, A and E, B and D, C and D, and C and E. Is there a direct flight from A to D? Can you fly from A to D with 1 stop? With 2 stops? In order to solve this problem, we can draw the following simple picture. First, I'll draw a circle for every city in the country. I'll have 5 circles for A, B, C, D, and E. And now, if there is a direct flight between 2 cities, I'll connect these 2 circles by a line. And I see there is no line between A and D, which means there is no direct flight from A to D. But I can fly from A to D with a stop at B or with a stop at C. There is also a flight with 2 stops, which will go through E and C. In Guarini's puzzle, we are given a 3x3 chessboard with 2 black knights and 2 white knights. And our goal is to exchange the places of the black and white knights. But first, let me remind you that a chess knight can move in an L shape in any direction. That is, it can make 2 steps horizontally and then 1 step vertically, or 2 steps vertically and then 1 step horizontally. For example, a chess knight in the center of a 5x5 chessboard can go to any of these 8 locations. Now let's get back to Guarini's puzzle. Can we exchange the places of the white and the black knights? First, let's enumerate all the cells of this chessboard. Actually, not all of them. We don't need the central cell because a knight can never get there. So we have 8 good cells. And now we'll connect a pair of them by a line if the knight can get from one cell to the other one in one move. This is what it looks like. Now I'll draw the same thing on the right hand side, where circles again correspond to the cells of the chessboard, and 2 of them are connected by a line if and only if a knight can make a move from one of them to the other one. I have 2 white knights in positions 1 and 3, and I also have 2 black knights in positions 6 and 8. And my goal is to exchange their positions. Can I do it? Of course, for example, I can move all of them counterclockwise until the white ones get to the positions 6 and 8 and the black ones get to the positions 1 and 3. For example, my first move would be to move this white knight by 1 position counterclockwise. Now I move the remaining 3 knights in the same direction. Now I make 1 more rotation like this, and then 1 more, and now the final one. And now I have 2 white knights in the positions 6 and 8 and 2 black knights in the positions 1 and 3. Exactly what I wanted to do. Now try to use the same graph to solve other Guarini's puzzles. We are now in the 18th century Königsberg in Prussia. There are 7 bridges, as you can see on the map, and a favorite evening activity of the local people was to plan a walk which would go through every bridge exactly once. But in 1735, the famous Swiss mathematician Leonhard Euler proved that it's impossible. And that was the first result of the graph theory. This is where graph theory originates from. Let's see why it's impossible. Here is a map of Königsberg. Clearly, we can ignore all roads and buildings on this map. They are not important for our goals. So we can simplify this map and just look at this new one, where we have 4 pieces of earth connected by 7 bridges. We can actually forget about the original map. This new one is equivalent to the original one for our goals. We can also give names to these 4 islands. Let's say this one is called B, and these 3 ones are called A, C, and D. Now, as always, I'll draw 4 circles such that each circle corresponds to an island in the original map. and I connect two of them by a line if and only if there is a bridge between two of them. For example, there is a bridge between B and C, so I connect them in my new drawing. And I also draw the remaining 6 bridges. Those connections are often called edges. So now we want to find a path which goes through each edge exactly once. Such a path is called Earlian path. It's named after Euler because he was the first one who discovered all this beautiful theory. Let's look closely at Earlian path. It has some start point and some end point. Let's look at the points in the middle. We enter each point once and leave it once, so we have at least 2 bridges connected to this point now. We can later enter this point one more time, but we will leave it as well. And we will have 4 bridges and 4 neighboring points. Now we can enter it one more time and leave again. In this case we have 6 neighbors, which means that in Earlian path every point except for the start point and the end point have an even number of neighbors. Now let's look at our original problem. We have 4 points and each of them has 3 neighbors. 3 is an odd number. There is no Earlian path in this drawing, because if there was one, then every point except for maybe 2 would have an even number of neighbors, which is not the case here. This is exactly how Euler proved that there is no walk crossing each bridge exactly once in Königsberg. Today, Königsberg is Kaliningrad in Russia, and some of the 7 bridges were destroyed during the war and some new ones were recently erected. So now there are 6 bridges in Kaliningrad. Can we find a walk which crosses each bridge exactly once now? Okay, first let's again draw these 4 points and connect a pair of them by a line if there is a bridge between them. So we can work with this picture now. And we see that 2 points here, B and D, have odd numbers of neighbors. Now, if there is an Eulerian path in this picture, then B and D must be the first and the last points in that path. Let's try to find such a path. Let's start with B and go to A. Then we'll go to C, to D, then maybe to B, to C, and to D again. We succeeded. We found a path which crossed each bridge exactly once. So now, in Kaliningrad, it is possible. In this lesson, we'll define graphs and we'll see many examples and applications of graphs. So what is a graph? To specify a graph, we need a set of objects. And objects can be arbitrary. It can be cities, islands, or maybe cells of a chessboard. And we'll also need a set of relations between pairs of objects. For example, flights between cities or maybe bridges between islands. And here's an example of a graph. This graph has 10 objects and 15 relations between them. Formally, a graph G is a pair of V and E, where V is a set of objects. We call them vertices or nodes. These two words are equivalent in graph theory. You can call them either vertices or nodes. And also we have E, a set of relations. We call each relation an edge. And E is a set of all edges of the graph. Here is a small example. We have 2 vertices and an edge between them. Of course, as always, we can give names to edges and vertices. For example, we can say that these 2 vertices are called U and V, and this edge is called E. Then we say that the edge E connects the vertices U and V. And U and V are endpoints, or just ends of the edge E. We say that the vertex U and the edge E are incident. Of course, the vertex V and the edge E are also incident. Also say that U and V are adjacent if they are connected by an edge. or will also be saying that U and V are neighbors, because there is an edge between them. Say I have four objects, A, B, C, and D, and I have four relations between them. One between A and C, one between D and A, one between B and D, and one C and B. So in the corresponding graph, I would have four vertices and four edges. I can draw this graph. I can draw a circle for the vertex A, a circle for the vertex B, one for C, and one for D. Now I connect pairs of them which correspond to the edges, right? There is an edge between A and C. I can draw a line between the circle A and the circle C. I can draw the edge AD, the edge BD, and the edge CB as well. This is what my graph looks like. But I could have drawn it differently, right? I could have said that here's my A, B, C, and D. In this case, my graph would look differently. This is what it would look like. But this is the same graph, right? It doesn't matter how exactly you draw your graph. Conceptually, they're the same graphs. Sometimes it might look nicer, or it might be easier to think about a graph drawn in a specific way. But again, conceptually, they are all the same. Okay, I also want you to note the following thing. I have the edge between A and C in my graph. What if I say there is, instead of this edge, there is an edge CA? It doesn't matter, right? It doesn't matter in which order I specify a pair of vertices. It is often convenient to consider directed edges. In this example, the edge goes from the left vertex to the right one, but not the other way around. Directed edges are also called arcs. We use them to describe asymmetric relations. For example, if there is a flight from A to B, but there are no flights from B to A, then we can use a directed edge. A graph which has directed edges is called a directed graph. Here's an example of a directed graph. Again, I have four objects, A, B, C, and D, and I have four directed relations. From A to C, I have an edge from D to A, from B to D, and from C to B. And here's a way to draw this graph. Note that when I specify an edge of an undirected graph, I use curly brackets, which means this is a set, so the order of two vertices doesn't matter. When I specify an edge of a directed graph, I use round brackets, which says here the order matters. For example, I have an edge from A to C, a directed edge. Now, if I change it to a directed edge from C to A, I change the way my graph looks like. As we have already seen, there are many ways to draw the same graph. And here is one more example. I give you this graph, and I give you that graph. Do you think they're the same? Do you think this is just two different ways to draw the same graph? Maybe. They both have 10 vertices and 15 edges, so they might be the same graph, just drawn differently. Okay, I will tell you that those are the names of the vertices of this graph on the left, and I also will give the same names to the vertices on the right. And now I'm telling you, if you check all 15 edges, in the graph on the left and in the graph on the right, you'll see the same 15 relations, which means those graphs are the same. They are just drawn differently. You can check, there is an edge between B1 and B3 in both graphs. There is an edge between A0 and A4 in both graphs. And you can check all 15 relations, they are the same. There is another way to draw this graph. This graph is again the same. You can check all 15 edges. And this is another way to draw this graph. Do you think these two graphs are the same? Well, they both have 10 vertices and 15 edges. They might be the same. But note that all vertices on the left have 3 neighbors, while here I show you a vertex which has 4 neighbors, while this one has 2 neighbors. So these graphs are definitely different. This is not just 2 different ways to draw the same graph. These graphs are different. They represent different relations between objects. There are many ways to draw a graph, and there is a field called graph drawing which studies different ways of graph drawing. The famous computer scientist Donald Knuth from Stanford University says that graph drawing is the best possible field I can think of. It merges aesthetics, mathematical beauty, and wonderful algorithms. Therefore provides a harmonic balance between the left and right brain parts. Let us see some examples of graphs in real life. The first example is the airlines graph. I have a map and there is an edge between two cities if and only if there is a direct flight from one to the other one. So for example, if there is a flight from Dakar in Senegal to Bissau in Guinea-Bissau, then I draw an edge between them. Edges here correspond to direct flights. Another example is the Facebook graph. Here vertices are people or maybe Facebook accounts. And two accounts are connected by an edge if they're friends on Facebook. For example, Joey and Chandler are friends, so they're connected by an edge. Here's one more example. Every scientist wants her paper to be cited by many other researchers. In the citations graph, we have vertices corresponding to papers and directed edges or arcs corresponding to citations. For example, if the paper by W. Olivas cites the paper by P. Clifton, then we draw a directed edge from the first one to the second one. If you write a program in, say, C++, then most likely you have many .h files or header files. Header files describe what functions you implement in your libraries. And there are many dependencies between them. For example, the tgmass header can use, or we call it include, the nlib header. And we can demonstrate it by a directed edge. Linked open data is a new way to structure data online. It helps to read large data by computers. It makes it readable by machines. And in a diagram for linked open data, we can draw a directed edge if there is an RDF or Resource Description Framework link from one point to the other one. And there are many other ways of using graphs in biology, biochemistry, and other fields. I bet you use graph applications almost every day. Let us see some examples. Say you're a big fan of the Beatles, and while visiting New York you want to go to Madison Square Garden from strawberry fields. Most likely you'll open some app on your cell phone and ask for the shortest path. And this very moment you use graph algorithms. You use algorithms which find shortest path between 2 points on a map. When you use Google or some other search engine, you also use graph algorithms. For example, the famous algorithm by Google, which is called PageRank, lets you see relevant links, but almost doesn't show you irrelevant pages on the internet. And the way it works is the following. It gives some score or rank to every page on the internet, so that you could see only relevant links in reply to search queries. Graphs are often used to develop good strategies for virtually any game. For example, in chess, you can come up with the following graph. Vertices would correspond to different positions, and there will be a directed edge from one position to another one if you can get from the first position to the second one making one move. For example, the most popular first move is either e2, e4 or d2, d4. There are, of course, like many other moves, and there are many more vertices in this graph. Here is a part of it. And for every position using this graph, you can estimate the score of the position. And using these scores, you can develop a good strategies. In the top part of this picture, you see a genome. But the current techniques only allow us to read short parts of the genome at random positions. And given these short reads, we want to assemble the original genome. Believe it or not, but in order to solve this problem, all the current techniques use graph algorithms. And later in this course, we'll see an example. A cell phone network usually has many stations, and each of them covers area which looks more or less like a hexagon. Roughly speaking, there are 4 frequency ranges, and neighboring stations better use different ranges. Is it possible to assign frequency ranges to stations such that no pair of neighbors uses the same one? Well, in this case, in the case of Iran, it is possible. We'll see why it is always possible to do so. When you produce computer chips, you want to make connections between elements of the circuit shorter. There are millions of transistors and other elements, and there are millions of connections between them. And it's much cheaper to produce such circuits if the connections are short and non-intersecting. We'll see this problem later in the course. In this lesson, we'll learn main definitions used in graph theory. Basically, the goal of this lesson is to make sense of the following sentence. An isolated vertex forms a component. Don't worry if this sentence seems ridiculous to you. By the end of this lesson, we'll see what it means in graph theory. The first definition is the degree of a vertex. In the Facebook graph, for example, the degree of some vertex is just the number of its friends. We can define it formally. The degree of a vertex is the number of its incident edges. Or in other words, it's the number of its neighbors. We denote the degree of a vertex V by deg of V. And also we say that the degree of a graph, or the maximum degree of a graph, is the maximum degree of its vertices. Let's see some examples. The degree of vertex V in this example is 6. It is connected to 6 other vertices. And the degree of the vertex V6 is 1, because it's only connected to V. In a cycle, every vertex has degree 2, because it's connected to the previous vertex and to the next one. Let us see one more example. In this graph, this is one graph. In this graph, the degree of the vertex V2 is exactly 2. The degree of vertex V8 is 1. But the degree of vertex V0 is 0. This vertex is not connected to anything. It's not incident to any edge. Such a vertex is called an isolated vertex. Again, a vertex of degree 0 is called an isolated vertex. A graph is called regular if all vertices have the same degree. For example, in this graph, the degree of every single vertex is 3. So this graph is regular. Also, if the degree of every vertex of a graph is k, we call it k-regular. So we can call this graph 3-regular. We have some graph G, then the complement of this graph, which is usually denoted by G bar, is the graph with the same set of vertices as G, which contains an edge if and only if G doesn't contain this edge. So the complement of G contains all edges which do not belong to G. In other words, the edge UV belongs to the graph G bar, or the complement of G, if and only if the edge UV does not belong to the original graph G. Here's an example. On the left we see some graph G, and on the right we see its complement. For example, in the original graph, the vertex V1 is connected to V2, V3 and V4. In its complement, it's connected to the other vertices, to V5 and V6. Similarly, V3 in the original graph is connected to all vertices but V5. And this is why in G complement, V3 is connected only to V5. A path in a graph is exactly what you think a path is. For example, if we have a graph of a city, then a path is a way to get from one point to another one. There are many different paths, and some are shorter, some are longer, and in graph theory and in real life too, we often want to find the shortest path between 2 points. In order to formally define a path, we need to start with a walk. A walk in a graph is a sequence of edges such that each edge starts in a vertex where the previous edge ended. And the length of a walk is a number of edges in it. Note that a walk can take the same edge several times. But a path is a walk where all edges are distinct. In a path, you never take the same edge twice. All edges are distinct. Although a path can go through the same vertex several times, a simple path is a path where all vertices are distinct. You never return to a vertex you already have visited. Now let's see some examples. Here is a graph, and for convenience every vertex and every edge has a name. And here's an example of a walk. You can start from the vertex V6, take the edge E1, then edge E2, E4, E5, E3, E1. You see every edge starts exactly where the previous one ended. So it is a walk. And the length of this walk is 6 because there are 6 edges in it. But we take the edge E1 twice. So this walk is not a path. In path, all edges are distinct. And here is an example of a path. You take the edge E7, then the edge E6, E4, and E5. The length of this path is 4, and clearly it is a walk because you always start where the previous edge ended, and also all edges are distinct. So it is a path, not only a walk. But it's not a simple path, because we visited the vertex V2 twice. A simple path has all vertices distinct. And here's an example of a simple path. Take the edge E7, then E6, E2, and E3. Every edge starts where the previous one ended, all edges and all vertices are distinct, so we call it a simple path. And the length of this path is 4 because there are 4 edges in it. Okay, sometimes it's convenient to specify a path not by a list of edges, but by a list of vertices. For example, I can say that there is a path V4, V5, V2. It is the same as say there is a path with edges E2 and E4. Note that although in this list there are 3 vertices, the length of the path is still 2, because the length of the path is a number of edges in it. 3 vertices, but 2 edges, so the length is 2. Similarly, we can define cycles. A cycle in a graph is a path whose first and last vertices are the same. You start somewhere, you go and return to the original vertex. This is a cycle. Note that a cycle can never have the same edge twice, because cycle is a path where the first and last vertices are the same, and all edges in a path are distinct. So all edges in a cycle must also be distinct. And a simple cycle is a cycle where all vertices are distinct except for the first one, which must be the same as the last one. This is a cycle. But you can only take this vertex twice, in the very beginning and in the very end. So a simple path is a path where all vertices are distinct, and a simple cycle is a cycle where all vertices are distinct except for the first one, which has to be taken twice. Here are some examples. The same graph. Here we have a cycle of length 6. We take the edge E2, E3, then E8, E4, E7, E6. We started from the vertex V5 and we ended there. So it is a cycle. It doesn't take any edge twice. It is a cycle. But it visits the vertex V5 3 times. So it's not a simple cycle. But this is a simple cycle. You take the edge E5, then the edge E4, E2, and E3. You started in the vertex V3 and you ended there. It is a cycle. You've never taken the same vertex twice except for the first one. So it is a simple cycle. Now we'll study connected components of graphs. For example, if in our graph we have some islands from Philippines, then you see there are roads on islands, so you can drive from one city to another city on the same island. But you cannot drive from one island to another one. So in this case, a connected component is an island, because you can easily travel within a connected component, within an island, but you cannot get to a different connected component. Let us define them formally now. First of all, we call a graph connected if there is a path between every pair of its vertices. In other words, if from any vertex you can go to every other vertex, then this graph is connected. This is a very natural definition. A connected component of a graph is a maximal connected subgraph of it. Subgraph means some part of a graph, a possibly smaller part of the original graph. It must be connected, and also it must be maximal. This means that it is not contained in any larger connected subgraph. Because if you know that this part is all connected, if this is connected component, you cannot say that its tiny subgraph is also a connected component. No, it must be maximal. If this thing is all connected, then this is a connected component. This is what maximal here means. Let's see examples. Here's a graph of 9 vertices. And V1, V2, and V3 are connected. They form a connected subgraph. But this is not a connected component, because there is a larger connected component. The vertices V1, V2, V3, V4, V5, V6 form a connected component. They are all connected, and you cannot extend it to a larger connected subgraph. But V1, V2, and V3 is not a connected component because it's not maximal. You can extend it to a larger one. Similarly, V7 and V8 form another connected component. And the vertex V0 itself forms the third connected component. And in general, if a vertex is not connected to anything, then it forms a connected component. And we know that these vertices of degree 0 are called isolated vertices. So every single isolated vertex forms a separate connected component. This is exactly the sentence we started this lesson with. We have already seen that sometimes it's more convenient to consider directed edges and directed graphs. For example, if we have one-way streets, then we want to be able to say that there is a street from here to there, but not the other way around. Or in social networks, if someone follows you, you don't have to follow him. This is an asymmetric relation, and we use directed edges and directed graphs to describe it. In an undirected graph, we denote an edge by a pair of its vertices in curly brackets. Curly brackets mean a set, and there is no order of elements in sets. So in curly brackets, u, v or v, u, they both mean the same undirected edge. But when we specify a directed edge, we use round brackets. And round brackets always mean that the order matters. For example, the arc of the directed edge from u to v is different from the arc or directed edge from v to u. If we have a directed edge from u to v, then we say that u is its tail and v is its head. And also, if we have both directed edges between u and v, the one from u to v and the one from v to u, then it is equivalent to one undirected edge, because it also says that you can go from u to v or from v to u. So sometimes in directed graphs we can just draw an undirected edge, which means that we have both directed edges between this pair of vertices. We define the notion of vertex degree only in undirected graphs. In directed graphs, there are 2 degrees for each vertex. The in degree of a vertex is the number of the edges ending at V. And the out degree of a vertex is the number of edges starting at V or leaving V. Here's an example. In this example, the in degree of V3 is 3 and the out degree of the vertex with 3 is 1. Because there are 3 edges which start at vertices V2, V1 and V4 that end at V3. And there is only one edge V3, V4 which starts at V3. Similarly, the in degree of the vertex V1 is 1 and the out degree of the vertex is 2. We can also define path in directed graphs, and this is basically the same thing just as in undirected graphs, just each directed edge should start at a vertex where the previous directed edge ended. So for example, V2, V3, V4 is a path of length 2. But V1, V3, V2 is not a path because there is no directed edge from V3 to V2. These 3 vertices don't form a path. Sometimes we want to associate a number with every edge. For example, here is a map of Spain, and on top of every road we see estimated driving time. This is an example of weighted graph. Here is another example. We have a regular graph, but now we can write a number for every edge. This is the weight of the corresponding edge. Such a graph is called a weighted graph. A directed graph can also be weighted. So a weighted graph gives a weight to every edge. The weight of a path, then, is just the sum of all edges on this path. And the shortest path between 2 vertices is just a path of the minimum weight. For example, if weight in our graph corresponds to the length of the path between 2 vertices, then the shortest path in this graph would correspond to the shortest path between these 2 points. And we define the distance between 2 vertices as the length of the shortest path between them. Here are some examples. Say we want to find a short path from V1 to V6. So here is some path. It's of length 11. It goes from V1 to V5, then to V4, and then to V6. Since the weight of the edge V1, V5 is 5, the weight of the edge V5, V4 is 2, and the weight of the edge V4, V6 is 4, we get the total weight 11. So the weight of this path is 11. Here is a path of length 12. It goes through vertices V7 and V4. And here is a path of length 13. It goes all the way to V2, then V7, V4 and V6. And here is a path of length 3. It just goes from V1 to V3 and from V3 to V6. And actually this is the shortest path between V1 and V6. In this lesson we will see several interesting classes of graphs. We'll start with path graphs, cycle graphs and complete graphs. We already know what a path in a graph is, but there are whole graphs called path graphs. The path graph of size n, which we denote by Pn, has n vertices and n-1 edges. The first edge connects the first vertex and the second one. The second edge connects the second vertex and the third one. And so on all the way until the last edge connects the penultimate vertex with the last one. Here is an example of the path of length 5, the P5. And this is the path of length 2. Here is the path of length 9. And we can obviously draw it in many different ways. For example, like this. So a path graph is just a path and nothing else. A cycle graph is a path graph where we also add an edge which connects the last vertex and with the first one. So the cycle graph of size n, which we denote by Cn, has n vertices and n edges. First edge connects the first two vertices, the second edge connects the second vertex with the third one, and the last edge connects the last vertex with the first one. Here is an example of C5 with a cycle of length 5. It differs from P5 only by one edge which connects V5 with V1. Here is another way to draw C5. This is a cycle of size 3. We also call it a triangle. This is a cycle of size 9, C9. It differs from P9 again only by one edge between V9 and V1. The complete graph of size n, or the clique of size n, which we denote by Kn, has n vertices, and for every pair of vertices it has an edge. Between every two vertices there is an edge. If you count the number of edges in this graph, you get n times n minus 1 over 2. Here you see the clique of size 6, the complete graph on 6 vertices. And this is the clique of size 5, complete graph on 5 vertices. Complete graph on 3 vertices is just a triangle again, so it equals C3. And the complete graph on 2 vertices is just one edge. It equals, for example, P2. Now we'll study trees. Here is the first problem. Remove the minimum number of edges such that there is a unique simple path between every pair of vertices. We want to remove some edges from this graph, the minimum number of them, such that for every pair of vertices there will be only one path, or one simple path. Okay, for example, there are currently two paths between V4 and V5. There is just an edge V4, V5, and there is a path which goes through V3 and V2. So we have to get rid of one of this path. For example, we can just remove this edge V3, V4. Now we have only one path between these two vertices, V4 and V5. But we still have two paths between V1 and V2. Just a direct edge and a path which goes through V5. Okay, we can remove the edge V1, V2, say. And now you can check that there is only one path between every pair of vertices. Let me now define a tree graph. A tree is a connected graph without cycles. There is an equivalent definition of a tree. A tree is a connected graph on n vertices and n minus 1 edges. Apparently, these two definitions are equivalent. Moreover, there is a third useful equivalent definition of a tree. A tree is a graph with a unique path between every pair of vertices. If there is only one simple path between every pair of vertices, this graph is a tree. We'll later prove that these three definitions are equivalent, but now we'll use them. Here is an example of a tree. How can we check that this is a tree? Clearly, this is a connected graph, and there are no cycles. You can check. You cannot start with a vertex and get back to it by using distinct edges. There are no cycles and it's connected. So by the first definition of a tree, it is a tree. By the second definition, which says that a tree is a connected graph on n vertices and n minus 1 edges, it is also a tree because it has 9 vertices and 8 edges. It is a connected graph with n equals 9 vertices and n minus 1 equals 8 edges. And the third definition says that it's a tree if there is a unique simple path between every pair of vertices. We can check it. For example, I want to find a path from this vertex to this vertex. You can check that there is only one path which goes like this. Or say I want to go from this vertex to that vertex. I'll take this edge, this edge, this edge, this edge, and this edge. You can check that for every pair of vertices, there is only one path between them. There is only one simple path here. Okay, this is why these graphs are called trees, because they look like branches of a tree, especially if you rotate them. A path is always a tree, because it's a connected graph without cycles, or it is a connected graph on n vertices with n-1 edges. And it also looks like a tree if you rotate it. Here is another tree. You can check it's a tree by any of these definitions. You can always choose an arbitrary vertex of a tree and call it the root of this tree. And now when you have a root, you can, for example, draw a tree in the same way that we saw on the previous slide. You can draw the root somewhere in the top level, then on the second level you draw all neighbors of the root, all vertices which are in distance 1 from the root. Then you draw, in the next level you draw all vertices which are in distance 2 from the root, which are neighbors to the vertices on the first level. This is one way to draw a graph, or to draw a tree. And here we have chosen some vertex which we call a root. You could have chosen any other vertex and draw it differently. So this is this tree, and here it's clear why a tree always has n-1 edges, because every vertex here has exactly one what we call parent. It has exactly one vertex on a level right above it, which is connected to it. For example, V7 is connected to V9. Every vertex has this parent except for the root. Okay, now I want you to remove the minimum number of edges from this graph such that there is a unique simple path between every pair of them. Now we know that if a graph has a unique simple path between every pair of vertices, then it is a tree. And we also know that a tree is a graph on is a connected graph on n vertices with n-1 edges. So we can just remove edges from this graph until we are left with only 4 edges, but we also have to keep it connected. So for example, I can remove this edge, V1, V2. Now I can remove this edge, V1, V3. Then V1, V4. Can I remove V1, V5? No, I would lose connectivity. I cannot remove it. Okay, I'll remove this edge, V2, V3. And then this, V2, V4. And then V3, V4. I got a connected graph with 5 vertices and 4 edges. So it's a tree. So there is a unique path between every pair of vertices. And that's easy to see. If you want to go from V2 to V4, just go through V5. You want to go from V1 to V3, again, go through V5. A graph J is called bipartite if all of its vertices can be partitioned in 2 disjoint sets, L and R, such that every edge connects a vertex from L to a vertex from R. In other words, there are no edges within one part. There are no edges which connect a vertex from L to a vertex from L, or a vertex from R to a vertex from R. And such a graph is called bipartite, and L and R are called parts of this graph. Here's an example. I colored all vertices of one part red and all vertices of the other part blue. And you can see that every edge, like this one or this one, connects a red vertex with a blue vertex. In other words, there are no edges connecting to red or to blue edges. This graph is also bipartite. Let's see why. Let's color V5 red, then all of its neighbors must be in the other part. Let's color them blue. None of them can be in the red part, because then there would be an edge which connects 2 red vertices. We can't have such a thing in a bipartite graph. So we color them blue, and all their neighbors must be red for the same reason. So actually this graph is bipartite. I can draw it in a different form, in this way. I put all the red vertices on the left and all blue vertices on the right. And now I draw all the edges of my graph. You see, it is bipartite. If every vertex from one part is connected to every vertex from the other part, then we say that this bipartite graph is complete. Let me remind you that a complete graph on n vertices is denoted by Kn. And a complete bipartite graph on L and R vertices in its parts is denoted by K, L, R. For example, this is a complete bipartite graph where one part has 2 vertices, the other one has 3 vertices. So we denote it by K2, 3. And here is a complete graph with 4 vertices in one part and 3 vertices in the other part. So we denote it by K4, 3. A cycle of length n for even n is always bipartite, because I can color all odd vertices blue and all even vertices red, and then every edge will connect a blue and a red vertex, so it is bipartite. But for odd n, cycles of size n are not bipartite, because if I put the first vertex in the L part, the second vertex in the R part, then the third vertex has to go to the L part, the fourth has to go to the R part, and the fifth vertex cannot go to L nor to R, because it is connected to vertices from both of them. So a cycle of odd lengths is not bipartite. Trees are always bipartite. One way to see it is the following. We know that we can draw every tree in this layered way, such that on the top we have some root vertex, then the next layer we have only vertices connected to the root, and this next level we have vertices connected to the previous layer, and so on. So we can color the first layer red, the second layer blue, the third layer red, and so on, and then each edge will connect a red vertex with a blue vertex. So trees are bipartite. Here's another way to draw the same tree from the previous slide.
Hello and welcome to the next module of the Graphs class. We started with the well-known handshaking lemma. Before stating this lemma formally, let's revisit the following puzzle. We're given 9 points, and we would like to connect some pairs of them by segments so that each point is connected to exactly 5 other points. Okay? To try to understand whether it is possible or not, let's just start connecting points by segments. So for example, if we connect these 2 points by segment, then each of them now is connected to exactly 1 point. Now let's add one more segment, then we have 2 more points of degree 1, then another segment, and now we have a point of degree 2. But what is essential in this case is that the number of points whose degree is odd always stays even. Okay? Now let's just try to realize this. In this case we have 4 points of odd degree, right? So this number is odd. Now let's add another segment. In this case, what we get is that we get 2 new points of odd degree. Now the number of points of odd degree is equal to 6, which is still an even number. Now let's add another segment. Now these 2 guys are of degree 2 and 4, which is even. So all the points of odd degree are these ones, and its number is 4. So as you see, the number of points of odd degree always stays even. So it is even in the beginning when it is equal to 0, and then each time when we add a new segment, it either stays the same, or it increases by 2, or it decreases by 2. So it always stays even. And this is essential for this problem because it actually proves that our mission is impossible in this case. Because if we reach a situation when there are 9 points and all of them have degree 5, then this means that the number of points of odd degree is odd in this case. But we've just shown that it always stays even. And this actually formally proves that, that this task is impossible. And this is actually, in a more general setting, this is known as a handshaking lemma. So the real life statement of this lemma is the following. So before a business meeting, some of its members shook hands. Now, what we claim is that the number of people who shook an odd number of hands is always even. In graph terms, it is stated as follows. In any graph, the number of vertices of odd degree is always even. Okay? And this is actually a special case or a consequence of the following degree sum formula, which states the following. If you have an undirected graph and if you compute the sum of degrees of all its vertices, then what you get is exactly twice the number of edges, right? So the question is how it implies the handshaking lemma. Well, it implies it as follows. So if we had an odd number of vertices of odd degrees, then the sum of all degrees would also be odd. Why is that? Well, we have some number of vertices of even degree. So the sum of their degrees is of course even. This is just some number of even numbers. Their sum is always even. And then we also have some number of vertices of odd degree. If this number is odd, for example, we have something like 1, 3, and 5, then the sum of these numbers is odd. So the total degree, the sum of all degrees, is some even number plus some odd number, which gives an odd number. So what we would get is that 2 times e is even to some odd number, which cannot be the case, of course, right? Because 2 times e is always an even number. Right? Now let's prove the degree sum formula. So this is before proving, let's consider a toy example, and we will actually use this toy example to prove the formula. So this is a graph with 6 vertices and 8 edges, and all the degrees of the vertices are shown here. And indeed, if we compute the sum of all the degrees, it is 3 plus 5 plus 3 plus 2 plus 1 plus 2. It gives us 16, which is exactly 2 times the number of edges, 2 times 8. Okay? Now let's try to prove the formula. For this, let's do the following. Let's temporarily remove all the edges from our graph. Now the degrees of all the vertices are equal to 0 and the number of edges is also equal to 0. So in particular our formula works for this simple graph because the sum of all degrees is 0 and twice the number of edges is also 0. So 0 is equal to 0, so we are in a good shape in this case. Now let's start adding edges back one by one. So each time we add a new edge, we also update the degrees of the 2 corresponding vertices. So now we have just 1 edge and 2 vertices of degree 1. In particular, note that in this case, our formula still works. So the number of edges is 1, so twice the number of edges is equal to 2. On the other hand, the sum of all degrees is also equal to 2. Okay? Now we continue this process till we get our initial graph. Okay, so this is our initial graph. Now, it is important to understand the following. Each time when we add a new edge, first of all, the quantity 2 times e always grows exactly by 2, right? Just because when we add an edge, e grows by 1, which means that 2 times e grows by 2. On the other hand, when we add a new edge, the total degree, namely the sum of all degrees, also increases by 2. Right? This is just because when we add an edge, we increase the degree of this vertex by 1 and of that vertex by 1. So we have 2 quantities, the sum of all degrees and twice the number of edges. Initially, they are both equal to 0. Then we start adding edges, and each time when we add a new edge, this one increases by 2 and this one increases by 2. So they always stay the same. Okay, so what just happened is that we proved the degree sum formula by induction on the number of edges. Our base case was an empty graph, a graph without any edges, right? When the number of edges is equal to 0. In this case, the formula holds for trivial reasons. And then what we've proved by as an induction step, we showed that each time when we add a new edge, we increase the total degree by 2, and we increase twice the number of edges also by 2, which finally proves us the degree sum formula once again. We will now use graph theory to solve another toy puzzle and to introduce some new important concepts. Okay, so there were 20 students had an exam, and each of them solved exactly 3 problems. It is also known that each problem was solved by exactly 5 students. So the question is, what was the number of problems, at this exam? First of all, let me show you that in fact we do not need graph theory to solve this puzzle. Indeed, so to solve it, assume that each student wrote each of his or her 3 solutions on a separate piece of paper. Then we conclude that there were exactly 60 pieces of paper, so exactly 60 solutions. Let's now take all these 60 solutions and stack up all the solutions of the same problem. So we will organize our solutions into piles. So each of our piles contains solutions to exactly the same problem. So we know that there are some number of piles. The number of piles is exactly the same as the number of problems. And we also know that in each pile, the number of pieces of paper is equal to 5, because for each problem there are exactly 5 solutions. So we have some number of piles. In each pile there are exactly 5 pieces of paper, and the total number of pieces of paper is equal to 60, which means that the number of piles is equal to 60 divided by 5, that is just 12. So the number of problems is 12. So this is the answer. So as you see, we do not need graph theory. At the same time, let me show you that it is natural to use graphs here. Okay, so to construct a graph here, let's introduce a node for each of our 20 students. They are shown here on the left. On the other hand, let's introduce a node for each of our problems. Let's pretend that at this point we still don't know the number of problems, and let's denote them by k, the number of problems by k. Okay? Now let's do the following. Let's connect each of our 20 students with 3 problems that was solved by this student. Okay, so for example, this bottom student solved the following 3 problems, and some other student solved the following 3 problems. In general, the picture looks as follows, and in fact, the exact structure of this graph is not so important for us. What is important for us is that this is a bipartite graph. So each edge, in our case, joins a node on the left with a node on the right. This allows us to compute the number of edges in 2 different ways. On one hand, we know that the number of edges is equal to 20, which is just the number of nodes on the left, times 3, just because the degree of every node on the left is equal to 3. And we know that each edge goes from left to right. Okay? On the other hand, we can do the same, exactly the same with the right part. So we know that on the right we have k nodes, and the degree of each of its nodes, of these nodes, is equal to 5, which means that the number of nodes is equal to 5k. So we have this equality, 60 is equal to 5k, and we conclude that k is equal to 12. Okay? Now let me take this chance to introduce the required concepts. So first of all, as I have mentioned already, the resulting graph is bipartite. So just by definition, a bipartite graph is a graph whose nodes can be partitioned into 2 parts, such that in each of these parts there are no nodes. There are no edges, So every edge joins some node from the left part with some node from the right part. So this is a bipartite graph by definition. So in this graph, we used the technique known as double counting to solve our problem. Namely, we counted the number of edges in 2 different ways. On one hand, we showed that the number of edges in such a graph is equal to the total degree of the left part, where the total degree is just the sum of all degrees of the vertices or of the nodes on the left. On the other hand, by exactly the same argument, it is equal to the total degree of all the nodes on the right. This allowed us finally to compute the number of nodes in the right part. Hello and welcome to the next lesson of the graph class devoted to connected components. To motivate the study of connected components of graphs, let's consider the following two seemingly unrelated puzzles. The first one is called the heaviest stone. The setting in this puzzle is the following. We're given n stones, and we have an expert who is going to convince us that some of these n stones is the heaviest one. For this, she is going to use pen balance. Namely, at each iteration, she is going to take two stones and to put them on the pen balance, and the pen balance will show that, for example, in this case, this stone is heavier than that one. Okay? So the question is, what is the minimum number of such comparisons needed to convince everybody that some particular stone is indeed the heaviest one? Okay? The next puzzle is the puzzle that you've seen already. It is called Guarini puzzle, and in this case the question is the following. We're given a 3x3 board in which in one setting we have two white knights at the top row and two black knights at the bottom row. And the question is whether it is possible to move the knights to actually swap the knights finally. Namely, to get two black knights at the top row and two white knights at the bottom row. And we know already that this is indeed possible, right? On the other hand, we know already that if the initial configuration is such that we have white knight here and black knight here, and also black knight here and white knight here, and we would like to reach a situation where we have two black knights at the top row and two white knights at the bottom row, then this is in fact impossible. So we've actually shown this by analyzing the corresponding graph. But the question now is whether it is possible to implement a simple program that will check this for us. So instead of trying to understand whether some configuration is reachable from some other manually, we would like to do this automatically. Okay? So these are two seemingly unrelated puzzles, but as you might have already guessed, we will show that both of them can be solved by analyzing the connected components of some underlying graph. Okay? Now let me switch to defining the connected components. For this, first consider the following maze. Now in this case, it is just simply a grid with walls between some of the neighboring cells. Now it is not so difficult to see that in this case there are three connected regions shown here in red, blue and green. And by saying that some region is connected, we mean that from any cell you can any cell is reachable from any other cell. So any green cell is reachable from any other green cell. And the same for blue region and the same for red region. On the other hand, all these three regions are different, meaning that if we're given a cell in a blue region, for example, then we cannot reach a cell in a green region. Okay? And of course, there is also an underlying graph in this case. So to show this, let's introduce a node for every cell in our maze. Okay? Now let's connect by edges any two neighboring cells such that there is no wall between them. Okay? This will give us the following graph shown here on the slide. Now let's forget about the initial maze and let's just focus on this graph. Again, it is not so difficult to see that this graph consists of three connected components, right? And these connected components are essentially the same as were in our maze. Okay? So let me now try to formalize this notion, and let me also specify that in this video we are working with undirected graphs. Okay? So for such a graph we say that two vertices u and v are connected if there is a path between u and v. Okay? Then first of all, it is not so difficult to see that this binary relation, to say it formally, is transitive. This means that if U and V are connected and V and W are connected, then U and W are also connected. Well, intuitively this is clear. Let me try to show this. So if we have U and V, vertices U and V, so they are connected, which means that there is some path in a graph. If on the other hand V and W are also connected, this also means that there is a path somewhere in our graph that connects V and W. But if you join these two paths, this will give you a path from U to W, right? Which means that U and W are also connected, okay? And also we say that a graph is connected if there is a path between any of its two nodes. Okay, so in this case it cannot be disconnected into two independent parts. Okay, there is a path between any two nodes. Also, now we are ready to define connected components formally. So connected components of a graph are just connected parts of a graph. So formally we say that any graph can be partitioned in, more formally, vertices of any undirected graph can be partitioned into parts called connected components, satisfying the following properties. First of all, each node of a graph belongs to exactly one connected component. Also, each connected component is connected, meaning that for every two vertices of a connected component, there is a path between them. And also, different connected components are disconnected from each other, meaning that if you have a node in one connected component and a node in another connected component, then there is no path in the graph between them. Okay? Let me now show you a small example. Now, in this case, we have 5 nodes and there are no edges. So initially, every node forms a separate connected component. So the number of connected components is equal to 5. Okay. Then, if we add these two edges to our graph, then the number of components drops to 3. So first 3 nodes form a connected component, and the fourth vertex forms a separate connected component, and the last vertex also forms a separate connected component. Finally, if we add 2 more edges, then the graph becomes connected. So in this case, the number of components is just equal to 1. We're now ready to show how to implement a program that will solve the GUI-Mini puzzle for us. Let me remind you once again the statement of this puzzle. In this case, we're given 2 configurations. For example, 3x3 board with 2 white knights and 2 black knights. And the question is whether one configuration is reachable from the other one. In other words, the question is whether we can move the knights so that to get the second configuration from the first one. Let me also remind you how we were able to solve this puzzle using graph theory. So in this case, there is an underlying graph connected to this board, which can be drawn as follows. So first, let's introduce a new vertex, a new node for every cell, except for the middle one actually, because it is not reachable by any knight here. So there are 8 essential cells in this case. Okay, then we connect 2 cells by an edge if they are within one knight move in this case. So this gives us the following graph with 8 nodes and 8 edges, and it is instructive to draw this graph like this, to untangle this graph. And if we untangle it, then we see that it is actually just a cycle with 8 nodes and 8 edges. So it is 6, 7 is connected to 3, then finally 3 is connected to 2. No, 3 is connected to 4, 6 is connected to 5, and 2, and 2 and 4 are connected to 8. So initially what we have is that here we have a white knight, and also we have a white knight here, then a black knight is at position 6 and another black knight is at position 8. Okay, and then it is not difficult to see that if we ask the knights to move around the cycle, either clockwise or counterclockwise, then we reach a situation shown here on the right. Okay, so we were able to solve this puzzle by analyzing the corresponding this graph. But what is more interesting is that there is another graph connected to this puzzle or this game. In this graph, let's do the following. Let's introduce a separate node for any possible configuration. And by saying configuration, I mean any 3x3 board with 2 white knights and 2 black knights, somewhere in some cells, except for the middle cell, which is in any case not reachable. Okay, so this is our configuration is going to be any such 3x3 board. And let's just imagine a graph where all the nodes are all such possible configurations. Okay, then let's do the following. Let's join 2 such configurations by an undirected edge if they are within a single knight move. Okay. As usual, this is best illustrated with an example. So here we show just 6 possible configurations. In fact, there are many more such configurations. So we have 6 of them shown here on the slide, and there are the following edges between them. Let's just try to understand what is the meaning of these edges. So for example, these 2 guys are connected by an edge, and as you remember, this means that they are within a single knight move. And indeed, in this case, to get from this configuration to that one, from left to right, we just move this black knight to the bottom right corner, right? And vice versa, if we would like to get from the right of these 2 guys to the left of these 2 guys, we just move this knight here, right? This means that they are within a single knight move from each other, right? Similarly, if we consider now these 2 guys, then we see that they only differ by moving this knight between these 2 cells, right? Similarly to these 2 guys, this one and this one, they differ just by moving the knight between these 2 cells, right? And so on. On the other hand, these two nodes are not connected by an edge because they are not within a single move from each other, right? So there is no edge between them because to reach one of them by the other one, from the other one, you cannot move just a single knight. At the same time, we see that one of them is reachable from the other one. For example, if you have this configuration and you would like to reach a configuration to the left of it, you can first move a knight to get this configuration, then you move a knight to reach this configuration, and finally you move a knight to reach the desired configuration. Okay, so there is a graph connected to this game, and then what remains to understand is that one configuration is reachable from some other configuration if and only if the corresponding 2 configurations belong to the same connected component in the corresponding graph. This in turn means that if you have a program which for a given graph computes connected components, then you can easily solve this puzzle just by constructing the corresponding graph, namely first by constructing all the nodes, then by joining some pairs of nodes by edges, and then just passing this graph to your black box procedure. Then what remains to be done is just to check whether the given 2 configurations lie in the same connected component. If they do, then one of them is reachable from the other one. If they do not belong to the same component, then this is actually a proof that one of them is not reachable from the other one. We will now prove a simple lower bound on the number of connected components in terms of the number of nodes in the graph and the number of edges in this graph. So the theorem states that for any graph G, the number of connected components in this graph is at least its number of nodes minus its number of edges. Okay, so we will prove this theorem in a minute, but now let's consider several special cases. First of all, if the graph is connected, then this theorem says that the number of edges in this graph is at least v minus 1. At least the number of nodes minus 1. Why is that? Well, assume for the sake of contradiction, then the number of edges is at most v minus 2. So it is strictly smaller than v minus 1. But in this case, this theorem would give us that the number of connected components in this graph is at least 2. But this is a contradiction with the fact that the graph is connected. Recall that the graph is connected, that if the graph is connected, then the number of connected components in this graph is equal to 1. Okay? So another extreme case is when there are no edges in our graph. So in this case, the number of edges is equal to 0, and in this case, the theorem states that the number of connected components is at least v, and in this case, it is actually equal to v, which makes perfect sense because if there are no edges in the graph, then each node forms a separate connected component. So if we have v nodes, then we have v connected components. Finally, let me also remark that if the number of edges is at least the number of vertices in our graph, then this theorem is useless. So the lower bound that it gives is that the number of connected components is at least some non-positive number, is at least 0 or at least minus 1, for example, or at least minus 2, which is actually obvious because the number of connected components is always non-negative, right? Now let's turn to proving this theorem. So again, what we're going to do is to first remove all the edges from our graph and then adding them back one by one. Okay, so if we remove all the edges, then what we have is v nodes. So initially we have v connected components, and our goal, remember, is to prove that the number of connected components is at least v minus e. So initially we have v connected components, and the quantity v minus e is equal to just v, right? Because e is equal to 0. So initially the inequality holds with equality. Okay, then let's see what happens if we add an edge to our graph when we start adding edges. So first of all, this quantity v minus e, each time when we add an edge, it decreases by 1, right? So e increases by 1 when we add a new edge, which means that v minus e each time decreases by 1. Okay, now our goal is to understand what happens with the number of components. So initially it is equal to v, and we will show that each time when we add a new edge in our graph, the number of components either stays the same or decreases by 1. So if we show this, if we show that each time it either stays the same or decreases by 1, it will prove the theorem. Why is that? Well, initially we have number of connected components on one hand, and we have this quantity v minus e on the other hand, right? Each time when we introduce a new edge, this quantity decreases by 1, and this quantity either decreases by 1 or stays the same. So in the process, what happens is the following. This one always decreases, and this one sometimes decreases and sometimes stays the same. So this one decreases faster than that one, and this actually proves that the number of connected components is always at least v minus e. Okay, so what remains to be shown is that each time when we introduce a new edge, the number of connected components either stays the same or decreases by 1. Well, consider these two cases. Either a new edge, which is shown here in orange or in brown, connects two nodes from different connected components, and this is exactly the case when the number of connected components decreases by 1. So in this case, before adding this edge, we had the following two connected components, and when we add the new edge, these two connected components actually merge into one, so the number of connected components decreases by 1. On the other hand, if the new edge joins two nodes that actually belong to the same connected component, then the number of connected components do not change. Okay? So initially we had these two connected components, and when we add this brown edge, they just stay the same, because the new edge just joins two nodes of the same connected component. And this finally proves our lower bound. We will now apply immediately the lower bound that we've just proved to solve the heaviest stone puzzle. So recall that in this puzzle we're given n stones of different weights, and the expert would like to convince us that some particular stone is the heaviest stone. Okay, so she knows the weights of all the stones, and what she is going to do is to use the pen balance to repeatedly compare some pairs of stones. And each time when she compares, the pen balance actually justifies that some of the stones, in this case this one, is heavier than that one, right? So the question is, what is the minimum number of comparisons? Let's now first try to prove some upper bound on the number of comparisons needed. Let's just, in a sense, let's design some protocol for justifying that some particular stone is the heaviest one. So one way of doing this in n-1 comparisons is to, for example, compare the heaviest stone with all the other n-1 stones. So indeed, if the expert takes the heaviest stone and repeatedly compares it to the first remaining stone, and to the second one, then to the third one, and finally to the n-1 one, then after all these n-1 comparisons, everybody is going to be convinced that this one is indeed the heaviest, because the pen balance will reveal that this one is heavier than that one, that one, that one, and so on. Okay, so in n-1 comparisons, we will convince everybody that that particular stone is the heaviest one. Moreover, we can actually, if we order all the stones by their weight in advance before making any comparisons, then in n-1 comparisons we can even reveal the full order of stones, of their weights, I mean. Because if we, for example, assume that we have n stones and they order it such that the first one is the lightest one, then the next one goes immediately after that one, and so on. So let's just denote for concreteness their weights by W1, W2, and so on, Wn, and assume that they order it like this. W1 is smaller than W2, which in turn is smaller than W3, and so on, which is smaller than Wn. Then we are going to compare the first two guys. This will reveal that the first one is indeed lighter than the second one. Then we are going to compare the second one and the third one. Okay, this will ensure that the third one is heavier than the second one, and so on. So in n-1 comparisons, we will actually reveal the full order of these n stones, and in particular, we will prove that the last one is the heaviest one, right? So in n-1 comparisons, we definitely can convince everybody that the given stone is the heaviest one. But still, the question is whether this is the optimal number of comparisons. Namely, can we somehow show that in any other such convincing protocol, the number of comparisons is at least n-1? And surprisingly, we will show this now using our lower bound for the number of connected components. And for this we need a graph, and the graph is going to be constructed as follows. Let's introduce a node for any stone. So it is going to be a graph on n nodes, and we will join two nodes by an edge if there was a comparison involving these two stones. Okay, so first of all, note that we are not even interested in the result of this comparison. We just reflect the fact that these two stones were compared. Okay, so this gives us a graph. And now a simple but crucial observation is that if there are less than n-1 edges, in this graph, then the number of connected components in this graph is at least 2. But this actually means that the court, everybody still know nothing about the relative comparison between this part of the stones and that part of the stones. Namely, if the situation looks as follows, so we have some number of stones. Let me draw them by these dots. And there were some number of comparisons involving involving these stones, and still we have two connected components, then the claim is that we still cannot be sure in which of these two parts the heaviest stone, to which of these two parts the heaviest stone belongs, just because we haven't yet compared any stone from the left part with any stone from the right part. So we know nothing about the relative order of these two parts. Okay, but to make it a little bit more formal, so I assume that the heaviest stone belongs to this component, and this is this one, okay, this bold vertex. And then we can actually change the weights of all the stones in the left part just by adding some huge number to the weights. If we add the same amount to these three stones, then these two comparisons, the results of these two comparisons do not change, right? But at the same time, it will mean that the heaviest stone now belongs to this component, right? So this is a formal proof, but intuitively it is not so difficult to see that if there are two groups of stones such that we never compared any stone from here to any stone from here, then we still don't know where is the heaviest stone. It might be in this part, it might be in this part, which finally proves, using our lower bound for connected components, that n-1 comparisons are first of all required to convince everybody, and as we know already, n-1 comparisons are also enough for convincing everybody that this particular stone is the heaviest one. We now turn to studying directed graphs, and in particular we start with considering an important class of graphs called DAGs, which stand for directed acyclic graphs. So just by definition, a directed acyclic graph, or just a DAG, is a directed graph without any cycles. So here on the slide on the left we see an example of a DAG. So it is indeed a directed graph and there are no cycles in it. On the other hand, on the right we see a graph which is directed on one hand, but on the other hand there are cycles in this graph. So for example, this has a cycle in it, right? So it is not a DAG. So DAGs arise in many applications naturally. So let me give you several examples. So first such example is a so-called citation graph. In this case, nodes represent papers, and we add a directed edge from that paper to this paper if that paper cites this paper. Okay, so in this case it is clear that if this paper cites that paper, then that paper was published before this paper, right? Which basically means that when we follow an edge, we go back in time, and this ensures that in this graph there must be no cycles, right? Another common graph is a courses prerequisite graph in some, for example, computer science curriculum. In this case, nodes are courses, and we put a directed edge from course A to course B if in order to take course B you first need to take course A. Okay, so course A is a prerequisite for course B. And more generally, there are many such dependency graphs. In the general setting, we introduce a node for any job or any item in to-do list, for example, and then we put an edge from, say, job A to job B. Whenever, in order to process the job B, you first need to process the job A. So this represents the dependency between A and B. So you cannot start processing B if you haven't yet processed the job A. Okay, so for such dependency graphs, it is important to answer the following questions. The following question: what is the right order of processing all the jobs one by one? Okay, so what do I say by the right order? I mean that we would like to satisfy all the constraints. So each time when if we have an edge from A to B, then we need to make sure that when we process the job B, then A is already processed. Okay, so what we would like to do is, in a sense, to linearize our graph. And first of all, it is clear that definitely impossible if there is a cycle in our graph. So if you have, for example, 3 jobs and there is a cycle between them, something like this, then definitely it is not possible to satisfy all these constraints. I mean, each time if you number these vertices, something like 1, 2, 3, and you process the jobs in this order, namely you first process this job, then you process this job, and then you process this job, then it will violate this constraint. Okay? So you this constraint says that when you start processing the job 1, you need you only need to do this after you already processed the job 3, but this constraint is violated in this case. So if there is a cycle, then definitely this is not possible. We do not expect cycles in dependency graphs. Okay? On the other hand, it turns out that if there is no cycle, then such an ordering is always possible, and in fact it is not so difficult to construct this ordering. Okay, we will prove it in a minute, but first let me introduce this notion formally. So we say a topological ordering of a graph, or a topological ordering of a set of vertices of this graph, is an ordering satisfying all the edge constraints. Namely, whenever there is an edge from U to V, then U goes before V in this ordering. Let me show you an example. So in this case we have 5 nodes in our graph, and on the right we have this ordering. As you see, the ordering can be specified just by placing all the nodes just in a line. In this case we say that some node goes before some other nodes in our ordering if it is placed to the left of that node, right? So what you see is that if we place all the nodes on the line, and then if we draw all the edges in our graph, then all of them must go from left to right. In this case, we say that this is a valid topological ordering. As we've just discussed on the previous slide, if there is a cycle in our graph, then there is no topological ordering. What we're going to prove now is that if there is no cycle, then there exists a topological ordering, and it is not so difficult to construct it actually. Okay, so this is our theorem. Every directed acyclic graph has a topological ordering. We're going to prove it as follows. We will show it on the next slide actually, that every directed acyclic graph has a sink. Okay, and the sink by definition is a node with no outgoing edges. Okay, this will allow us to proceed as follows. So there is a sink in our graph. So this is a node with no outgoing edges. This actually means that it is safe to put it to the end of our ordering. All edges actually only, for this node there are only incoming edges, no outgoing edges. So definitely from this node there will be no conflicting edges going to the left, because just there are no outgoing edges for this node. So it is safe to put it to the end of our ordering. When we put this sink vertex to the end of our ordering, we just remove it from our graph, and at this point it is important to realize that when removing a vertex or a node from a graph, from an acyclic graph, we cannot add any cycle, so it stays acyclic. Then in the remaining graph there is a new sink. We also extract it and put it to the end of our current ordering, and so on. So we repeat this procedure. Now let me illustrate this with a toy example as usual. So consider this graph on 5 vertices. In this case there are actually 2 things, A and B. Let's for concreteness take A and put it to the end of our ordering. Okay, so this is A. Now we remove it from our graph, and we see that there is an edge B. We see that there are no outgoing edges, so it is safe to put it to the left of A. Okay, so there will be no conflicts. Then the next, when we remove B, the next sink is actually C, and you see indeed that each time when we remove the current sink from a graph, in the remaining graph there is still a sink. Probably this sink was not a sink in the previous graph when we haven't removed the vertex, but in any case it is an acyclic graph and it has at least one sink. So in this particular graph, the sink is C, so we put it again to the end of our current ordering, we remove it, and now E is a sink in the resulting graph we added, and then in the remaining graph, D is the only remaining vertex, so it is definitely a sink because there are no outgoing edges for this particular graph. So this is how we constructed a topological ordering, and now what remains to be done is to show that every acyclic graph has a sink. We will do this by assuming the contrary. So assume that we have some acyclic graph, but somehow there is no sink in this graph. This actually means that for every node there is at least one outgoing edge. And this allows us to start to organize the following infinite walk in our graph. So just start from any node, and since there is at least one outgoing edge from this node, we can follow this edge. This will lead us to some new node. For this node, we also know that there is an outgoing edge, and so on. So we just start working like this. So from this node, we go to that node. For that node, we also know that there is at least one outgoing edge, so we follow this edge to go to some other node. And we repeat this process, and we can repeat this process to infinity. However, our graph is finite, which means that at some point some node is going to be repeated. Probably not the one that we started from, but definitely there will be a repeated node in this process. But this, as shown by this toy example, actually constructs a cycle in our graph, which contradicts to the fact that our initial graph is acyclic, and which finally proves our theorem that states that every directed acyclic graph has a topological ordering. We conclude this lesson with discussing connected components in directed graphs. As usual, let's start with a toy example. So this graph actually looks connected in the sense that it is not clear how to pull it apart, how to split it into independent parts like it was for undirected graphs, right? On the other hand, it is not so clear what we mean when we say that it is connected, because there is no path, for example, from the vertex A to the vertex C, as you see in this graph. Well, actually there is no path from any vertex to vertex C in this graph, because for the vertex C there are no incoming edges, right? So it turns out that the right way of defining connectivity in directed graphs is the following. We say that two nodes are connected in a directed graph if there is a path from the first of them to the second of them, and there is a path from that one to this one. Okay, so U and V are connected if there is a path from U to V and the path from V to U. Okay, taking this notion of connectivity into account, we can partition the vertices of any directed graph into the so-called strongly connected components, which satisfy more or less the same properties as connected components in undirected graphs. Namely, each node belongs to exactly one strongly connected component. Also, if you take any two nodes from the same strongly connected components, then they are connected. Let me recall what we mean by saying connected. We mean that for these two vertices there is a path from, well, let me denote them by U and V, so there is a path from U to V and from V to U. Okay? On the other hand, if you take any two vertices from different connected components, then they are not connected. But this means, in this case, that there is no path either from U to V or from V to U. Okay? Probably there is no path neither from U to V, neither from V to U. Okay? But it is not excluded that there is still a path in one direction. So if two nodes belong to different connected components, we only know that there are no two paths from V to U and from U to V. Okay? Let me now illustrate the strongly connected components from the graph that we've just that we've just seen on one of the previous slides. So in this case, there are 4 connected components shown here on the slide. So in particular, the node C forms its own connected component, as well as the node E. On the other hand, the nodes B, H, D, I, and A all belong to the same connected component, and let's check that indeed there is a path in any of 2 directions between any 2 nodes. For example, if we take the vertex H, we can always reach the node D, for example, and from H from D we can reach B. And on the other hand, and you see that there is a cycle, right? And also there is a cycle going through D, E, and A. So there are 2 cycles having a common node, and this basically means that any of these 5 vertices is reachable from any of the other vertices in this case, because going through this cycle you can always reach B, and then you can switch to the other cycle if needed. So for example, if you need to go from H to A, you first go from H to D, and then you go this way. Okay, so indeed for any of these, from any 2 of these 5 nodes, there is a path from the first one to the second one, and there is a path from the second one to the first one. The same holds for these 3 vertices, F, G, and K. So they actually lie on a cycle, and when there is a cycle, then indeed all these vertices from this cycle, they form a connected component, and probably there are some other nodes in this connected component, but let me at least show that if there are 2 nodes lying on the same cycle, then they lie in the same connected component. Well, it is easy to see because from U to V there is a path along this cycle, and also from V to U there is a path along this cycle, right? So whenever vertices stay on the same cycle, they lie in the same connected component. But as you see from this example, it is not excluded that there are several cycles in the same connected component. Well, in any case, any graph can be partitioned into such strongly connected components. And actually, if you contract all the vertices of the same connected component into one vertex, and if you only leave edges that connect a vertex from some connected component to a vertex from some other connected component, then what you get is a graph like this. It is usually called a metagraph, either metagraph, or sometimes it is also called a condensation of the original graph. And it is not difficult to show that this graph is going to be a DAG, meaning that there will be no cycles in this graph. And this is more or less clear because if there is a cycle, as you remember, then all the vertices should belong to the same connected component, but not to different. While in our metagraph, all the nodes correspond to different connected components. Okay, so to summarize, the nodes of any directed graph can be partitioned into strongly connected components with the following properties. Each node belongs to exactly one strongly connected component. If 2 nodes belong to the same strongly connected component, then there is a path from the first of them to the second of them, and from the second one to the first one. Okay? And if 2 nodes belong to different connected components, then either there is no path from the first one to the second one in the graph, or there is no path from the second one to the first one, and probably there is just no path between these 2 guys. Okay, or there is just a path in one direction, either from this one to this one, or from that one to this one. Okay, and if you contract all the strongly connected components, if you contract each strongly connected component into one node, and you only leave in your graph edges from joining nodes from different connected components, then what you get is a metagraph or condensation, and it is known to be a directed acyclic graph. Hello and welcome to the next lesson of the graphs class devoted to Eulerian and Hamiltonian cycles. As usual, we start by providing some motivational puzzle, which in this case is actually a simplified version of an important practical genome assembly problem. In this case, this is probably even an oversimplified version. So in the genome assembly problem, we are looking to reconstruct a long genome. A genome can be considered in this case as a long string consisting of symbols A, C, G, and T. It is extremely long. Usually it consists of millions or even billions symbols. The problem is that we cannot read the genome. What we can do is actually what current sequencing technologies allow us to do is to read a short fragment of a genome, and we can read many such short substrings of a genome, and they are called reads. They are usually roughly several hundreds symbols long. Then our goal, the problem of genome assembly, is to reconstruct the initial string by from many of its short pieces. So in this case, as a toy example of this problem, we consider the following problem. Our goal is to find a string whose all three substrings are the given one. So in this case, we are given 8 strings of length 3, and we are looking for a string whose all 3 strings are exactly the ones that are shown here. At this point, it should not be clear how it is all related to Hamiltonian cycles or Eulerian cycles, but it will be clear in several minutes. Okay, so let me first introduce Eulerian cycles. As you probably already know, an Eulerian cycle in a graph visits each edge exactly once. Okay, let me make several remarks about this definition. First of all, it works for directed and undirected graphs. The only difference is that in directed graphs, by a cycle or a path, we mean a path or a cycle that follows the directions of all the edges. Okay, so in undirected case, we can traverse any edge in both directions. In directed case, we can only traverse an edge in its direction. Okay, so there is also a related notion of an Eulerian path, and the difference between a path and the cycle is that a cycle should start and end in exactly the same node, while in a path may start at some node and stop at some other node. Okay. This is an example of a non-Eulerian graph. So in this case, it is not possible to traverse all the edges either by a cycle or by a path. Okay, and this is actually a graph from the famous Königsberg Bridges puzzle, where the graph theory actually started. Okay, and this is an example of an Eulerian path. Let me convince you that it is indeed an Eulerian. Well, all the numbers here show actually an order of traversing all the edges here in the graph. Let me just try to follow this path. So we go here, then we go there, then we go there, there. Okay, and we actually even stop at the same vertex where we've started. So this graph contains an Eulerian cycle. So the natural question is, of course, what graphs do have an Eulerian cycle and what graphs do not have Eulerian cycles? So the Eulerian theorem states that a connected undirected graph has an Eulerian cycle if and only if all the degrees of all its nodes are even. Okay? For the directed case, the theorem states that a strongly connected graph has an Eulerian cycle if and only if all its nodes are balanced. And by saying balanced, we mean that the in degree of each node is equal to its out degree. Okay? So some part of this theorem, of these two criteria, are actually easy to see. So if we have, for example, let's focus on the directed case. If we have a cycle that visits all the edges of the graph and then ends at the same vertex, at the same node, this actually means that for each node, the number of times we enter this vertex was the same as the number of ways we left this vertex, right? Which means that its in degree must be equal to its out degree. So once again, if there is an Eulerian cycle, then every node in this graph should be balanced. The difficult part, the not so obvious, let me say so, part is the opposite part. So what we need to show is that if all the degrees are balanced, then there is an Eulerian cycle. And this is exactly what we're going to do now. So we will focus on the directed case. So as we've just discussed, if some node is imbalanced, then definitely there is no Eulerian cycle. So what we're going to show now is that if each node is balanced, then there is an Eulerian cycle. And this is exactly the graph shown here on the slide. You can check that for every node here, its in degree is equal to its out degree. For example, for A, we have exactly one incoming edge and exactly one outgoing edge. For the vertex, for the node D, for example, we have two incoming edges. Let me show them. So these are two incoming edges and two outgoing edges. Okay? And the same for the vertex H. We have two incoming edges and two outgoing edges. Okay? So this graph is balanced, and our goal is to construct an Eulerian cycle in it. Okay? What we're going to do is just to go for a walk in this graph. Let's start walking from some node. In this case, let's start walking from A. So we walk from A to B, and then we walk from B to C. So since our graph is balanced, we always, when we enter some node, we always have a possibility to leave this node. This is just because the number of incoming edges to any node is equal to the number of outgoing edges. So what will happen during this walk is that at some point we will get out of edges. Right, so at this point we return back to A and there are no untraversed edges. Yes, let me also mention that of course we are only going to traverse edges that haven't been traversed previously. Okay, so at this point it seems that we are stuck. We returned to the node A. There are no untraversed edges connected to A on one hand, and on the other hand, unfortunately, we haven't yet constructed an Eulerian cycle. So we are just stuck at a vertex A. At the same time, note that at this point we just have a cycle, and also we do remember that our graph is strongly connected. This means that there should be at least one node on our cycle which is somehow connected to the rest of the graph. More precisely, there must be a node on our cycle for which there are outgoing untraversed edges. So in our case, one of such nodes is actually the node C. And also note at the same time that now we have a cycle, and for the cycle there is no beginning and no end, right? So we can start traversing this cycle from any of its nodes. For example, let's assume that we've started to traverse this cycle from the node C. Okay, it is convenient because we can, on one hand, for C there are still some outgoing untraversed edges. At the same time, going from C, we can easily traverse our cycle that was constructed previously. We start from C and we end at C, and then we continue traversing this. Right? This way, by shifting the starting point of our cycle, we make sure to glue some two cycles. I will tell about this more in a minute. So let's continue traversing our graph from the node C. So we go from C to D, we go from D to G, and from G to C. And now we are again stuck at the vertex C. Okay, let's now see what happened. On our first iteration, we started from node A and we constructed some cycle. Okay, this was very roughly, this is how our cycle looked like. Then we realized, so this was vertex A. then we realized that in our cycle somewhere there is a vertex C for which there are some other untraversed edges, and we found some other cycle. Okay, but then through this node C we can glue these two cycles, right? So because now we can consider, we can traverse these two cycles starting from the vertex C. So we start from here, we traverse the first cycle this way, and then we traverse this cycle this way. So this way we actually get a larger cycle. Okay, we first constructed some cycle and then we actually extended by gluing some additional cycle. And what we get now is still some cycle that visits some edges, and it is still not an Eulerian because there are still untraversed edges. But now we are going to repeat the same procedure. Now we have a larger cycle, and in this cycle there is a vertex G which still has untraversed edges. So we might assume that our brown cycle here, we started to traverse it from G, then we traverse on all the brown edges, and then we continue exploring the graph. So we go from G to H, and then we get back to G from H. Now we extended our cycle even further, and then we continue from the vertex D, which lies on our brown cycle on one hand. On the other hand, it still has some outgoing untraversed edges. And this way we extend our cycle finally to the Eulerian cycle. Okay, and this basically proves our theorem for the directed case. Okay, now the remaining question is what happens with path instead of cycles. It is actually not so difficult to reduce this criteria to the criteria of the existence of Eulerian cycles. First of all, if we are looking for a path in our graph, then of course not every vertex, not every node in our graph should be balanced, because for the path we have one outgoing edge. Probably we visit this node once more again, but then, so this basically means that for the starting vertex of our path, it has outgoing out degree, which is one more than its incoming degree, and the same is for the end of this path, right? Then, if you would like to get a criteria, first of all, in your graph, if there is an Eulerian path, then these two vertices should be uniquely definable and identifiable, right? So there should be a vertex whose out degree is 1 times larger than its out degree, and vice versa. For the end vertex, it should be a uniquely defined vertex whose in degree is 1 larger than its out degree. And then, but if you add an edge from this ending point to its starting point, then you will get a cycle. And basically then you can use a criteria for cycles. Let me illustrate this on a simple example. So imagine the following graph. So in this case, the in degrees and out degrees are as shown on the slide. So for example, for this vertex, its in degree is equal to 2 and out degree is also equal to 2. This vertex is also balanced and this vertex is balanced. On the other hand, for this vertex we have in degree equal to 1 and out degree equal to 2, which means that this is the only vertex that can be a starting vertex of an Eulerian path. On the other hand, for this vertex, its in degree is equal to 2, but its out degree is equal to 1, which means that it is exactly the vertex that should be the last vertex of an Eulerian path. Okay, now let me try to construct the corresponding Eulerian cycle here. We might, for example, go first here, then here, then here, then here, then here, here, and here. Okay, so indeed there is an Eulerian path in this graph. But if we would like just to find a simple criteria, then it remains to know that if we add the following edge from the uniquely determined end of the path to the uniquely determined beginning of the path, then what we get is actually an Eulerian cycle in the resulting graph. And for Eulerian cycle, we already have a criteria. So a criteria for a path in directed graph is the following. So there should be a uniquely determined beginning of the path. There should be a uniquely determined end of the path, such that if you add an edge between them, then the graph should become balanced. Okay? Okay, finally, let me conclude this video with mentioning that the method actually that we use to prove that there is an Eulerian path in this graph can be easily transformed into a program or into an algorithm. And indeed, for this problem for finding Eulerian cycles or paths in the graph, there are very efficient algorithms in practice. So even if in your graph there are millions of edges and millions of nodes, it is very easy to find an Eulerian cycle just in blink of an eye. We now turn to defining Hamiltonian cycles. So they are defined similarly to Eulerian cycles, but now our goal is to traverse all the nodes of a graph, but not all the edges as in Eulerian cycles. For example, this graph is actually Hamiltonian, meaning that there is a Hamiltonian cycle in this graph. And if you already tried to construct a Hamiltonian cycle for this graph by hand, you probably noticed that it is not so easy. So this is a Hamiltonian cycle in this graph, and it is not so difficult to check that it is indeed a Hamiltonian cycle. So it always traverses some edge on one hand, and it goes through all vertices of this graph exactly once. Okay? So the dramatic difference between Hamiltonian cycles and Eulerian cycles is that for Hamiltonian cycles we have no simple criteria known that would allow us to check whether a graph has a Hamiltonian cycle or not. So nothing like checking whether all the vertices are balanced or not is known for determining whether it has a Hamiltonian cycle or not. And more generally, there is no polynomial time algorithm known for finding a Hamiltonian cycle in a graph, or even for checking whether there exists a Hamiltonian cycle in this graph. So recall that for the Eulerian cycle problem, we have a very efficient algorithm. So we try in time is proportional to the number of nodes plus the number of edges of the graph. For Hamiltonian cycle, nothing like this is known. We don't even know how to solve this problem in the number of steps proportional to something like the number of nodes plus the number of edges to the power of 100, for example. We don't know how to do this. And in fact, this is the essence, the question of existence of such a polynomial time algorithm for the Hamiltonian cycle problem is the essence of the famous P versus NP problem, which is the most important problem in computer science, open problem in computer science. It is one of the so-called Millennium Prize open problem. For resolving this open problem, Klein Mathematical Institute provides a bounty of $1 million. So very roughly, to state this problem in probably 1 or 2 minutes, let me try to state it as follows. So P is the class of all computational problems that can be solved efficiently. This is in polynomial time. For example, Eulerian cycle problem is in the class P because we do have efficient algorithms for these problems. On the other hand, NP is the class of all computational problems for which we can verify a solution efficiently. What does it mean? Well, if I give you a graph, then it is not so clear how to find a Hamiltonian cycle. But if I give you a graph together with a Hamiltonian cycle, then you can easily check whether the given cycle is indeed a valid Hamiltonian cycle in this graph or not. So a solution can be easily verified both for Hamiltonian cycle problem and for Eulerian cycle problem. So we know that Eulerian cycle problem and Hamiltonian cycle problem lie in the class NP. But it is only for Eulerian cycle problems that we know that it lies inside the class P. So the question is whether the Hamiltonian cycle problem belongs to the class P of all computational problems that can be solved efficiently. We still don't know the answer to this question, and there is a bounty of $1 million, let me repeat, for resolving this important open problem in computer science. We conclude this lesson and the whole module on cycles in graph by revisiting the genome assembly problem. Namely, we are going to solve this puzzle, which is just a toy genome assembly problem. In this case, we are asked to reconstruct a string from all its strings of length 3, from all its substrings of length 3 over the alphabet A, C, G, T. As we've discussed already, this is just a small example of a genome assembly problem, and it is actually an oversimplification. In real life, when we assemble real genome, life is much more complicated because these strings are longer. The resulting string that we're looking for is of length millions or even billions, and reads contain errors. I mean, these substrings contain errors, and also there are many repeated elements and so on. But still, using this toy example, we will be able to demonstrate the main ideas used in modern genome assemblers. And as we've discussed already, we are going to use Hamiltonian cycles and Eulerian cycles to solve this problem. So in search for an inspiration for solving this problem, let's consider some known string, and let's consider all its 3 strings. For example, let's consider the word discrete and all its possible substrings of length 3. So what we see by looking at this example is that any 2 consecutive strings have an overlap of size 2. By saying overlap, we just mean a common part of size 2. So for example, the first 2 substrings, this is this and ISC, they have this common part IC, right? And this is of course true for any 2 consecutive strings. So for example, for CRE and RET, the suffix of CRE, it is just RE, is equal to prefix of RET, which is also RE. This just reflects the fact that all these 3 strings come from the same initial string, right? And this gives us the following idea. What we need to find is an order on our 3 strings such that if we place these 3 strings in this order, then there is an overlap of size 2 between any consecutive strings. For example, the initial order doesn't work because right after AGC goes ATC, and they do not have this overlap of size 2, right? So what we need to find is a permutation of all these 3 strings which satisfies this property that there is always an overlap of size 2 between any 2 consecutive strings. Okay, but this is actually a Hamiltonian cycle problem. Why is that? Well, because we can draw the following natural graph. Let's use our strings as nodes in our graph, and let's add a directed edge from this string to that string if there is an overlap of size 2 between them. Namely, if the suffix of this string of length 2 is equal to the prefix of length 2 of this string. Okay, let me give you an example. For example, in this graph there is a match from CCA to CAG exactly because the suffix of CCA is equal to 2, is equal to CA, I'm sorry, and the prefix of CAG of length 2 is equal to CA. So this edge basically reflects the fact that CAG potentially might follow CCA in this in the string that we are looking for. At the same time, there is no edge from GCA, for example, to ATC, because we know for sure that ATC should not follow GCA, okay? Because there is no overlap of size 2 between these 2 strings, okay? So we are looking for a Hamiltonian cycle in this graph, and this is a Hamiltonian cycle. And in fact, when you have a Hamiltonian cycle, it is not so difficult to reconstruct the string. So let's do this together. So we start with the string TCA. So at this point, we have just a string TCA. And then by traversing the cycle, the Hamiltonian cycle that is shown here, we will gradually extend our string till we get the resulting string. So from TCA we go to CAG, so we append G to our current string. From CAG we go to AGC, so we append C. Then we go to GCA, then to CAT, to ATC, to TCC, and finally to CCA, which finally gives us the resulting string. So let's just do a sanity check. Let's check. So the first substring is TCA. It is exactly what is needed. The second is CAG. This is our string. The next one is AGC. It is AGC, okay, GCA, GCA, then CAT, it is CAT is here, then ATC, ATC is here, then TCC, which is here, and finally CCA, CCA. So indeed, all the substrings of length 3 are exactly our initial substrings. So in fact, we solved the problem. But the issue with this solution is that in fact we reduced our problem of finding the unknown string to the Hamiltonian cycle problem. But the issue is that for Hamiltonian cycle problem we do not currently have a provably efficient solution. We do not have an algorithm or a program that solves Hamiltonian cycle problem for all graphs in practice of size, for example, up to 1 million or something. So unfortunately, a Hamiltonian cycle problem is still an intractable problem for us. So if a graph has millions of nodes and edges, we do not expect our current technologies to be able to find a solution quickly for such graphs. So we definitely need a different method to be able to solve the real genome assembly problem, where the number of these strings is counted in millions or even billions. And what we're looking for is also is a huge string of size millions or billions. Okay? So, and as you might have guessed already, Eulerian cycles are going to help us in this case. So in the graph that we constructed, it is the so-called overlap graph because, well, basically an edge represents an overlap. In this case, each of our input strings is represented by a node. Now, instead of this, let's use this beautiful and strangely looking idea. Let's try to construct a graph where each of our input strings is going to be represented by an edge, but not by a node. So this idea was initially proposed by De Bruijn, who was constructing a so-called universal strings. And then it was proposed by Pevsner, Tang, and Waterman to use this idea in genome assemblers. Very roughly, the idea is the following. We're going to represent each string, for example, CAT, as an edge from its prefix to its suffix. In this case, for CAT, it is going to be an edge from CA to AT. I will show you an example in a second, and before this, let me mention that exactly this idea is used in modern genome assemblers, in state-of-the-art genome assemblers. Okay, so this is how a De Bruijn graph looks like for our input strings. So these are our 8 input strings. As we've discussed already, we are going to represent each of the 3 strings as an edge in the corresponding graph. For example, AGC is represented as an edge from AG to GC. Okay, ATC is represented as an edge from AT to TC. Okay, and so on. So we have exactly the same number of edges as the number of input strings in our case. Now, what is important in this case is that now, in this case, we're looking for an order of edges. So what we would like to do is to traverse all the edges one by one. That is, we're looking for an Eulerian cycle. And these are very good news for us, because for Eulerian cycles, we have extremely efficient algorithms for finding an Eulerian cycle in practice. Let me also show you that an Eulerian cycle indeed spells a string that is needed for our purposes. So let's start from TC, and from TC we go to CC, and at this point we spelled the string TCC. Then we go from TCC to CA, and the string CC, the edge CC to CA spells a string CCA, so we add A to to our resulting string. And we continue in the same fashion until we traverse all the edges. Let's once again do a sanity check, and let's check that our string indeed contains all input strings. Okay, so the first string is TCC. This is TCC. The next one is CCA. This is CCA. The next one is CAG. So CAG. The next one is HEC. AGC. The next one is GCA. GCA is here. CAT. Then ATC. And finally TCA. Okay. It is also interesting to know that the solution that we got here is different from the solution that we got from the Hamiltonian cycle approach. This is just because for our problem the solution is not unique. It may be the case that there are many strings that satisfy the requirement that all its three substrings are exactly the given ones. And in particular, as you see here in the de Bruijn graph, there are actually more than one Eulerian cycles here. By spelling each of these cycles, you actually spell a different solution for our problem. Okay? So now let me summarize the whole lesson. First of all, the definition of Eulerian cycle is that, or Eulerian path, is that it visits every edge exactly once. While Hamiltonian cycle is required to visit every node exactly once. So the difference in the definition of these problems is very tiny, seems to be tiny. So we just need to traverse either all edges or all nodes. Okay? So these problems definitely look very similar to each other, but they differ dramatically from the computational point of view. For Eulerian cycles, we have a very simple criteria for checking whether a given graph has an Eulerian cycle. And we have a very efficient algorithm for finding Eulerian cycles, which will probably find us very quickly an Eulerian cycle in any graph, in practice consisting of millions of nodes and millions of edges. And we do not know anything like this for Hamiltonian cycle problem, and actually the existence of such a polynomial time algorithm is a big open problem in computer science. Finally, as we have shown by the genome assembly problem, the right problem formulation makes all the difference. So we first reduced our problem of reconstructing a genome from its unknown part to Hamiltonian cycle problem, but this leads us to nowhere because for Hamiltonian cycle problem we do not have polynomial time algorithm. But then we managed to reduce it to Eulerian cycle problem, and which allowed us to solve this problem much more quicker, and it is actually used in modern genome assemblers exactly because for the Eulerian cycle problem we do have efficient algorithms.
Hi everyone! This week we'll study properties of graph classes. We'll study trees, bipartite graphs, and planar graphs. Let's start with trees. And here is the first problem. The Hurricane Barbara destroyed all roads in a country, and we want to restore some of those roads such that every city is reachable from any other city. So I can get from every city to every other one, possibly going through some other cities. On every road you see its repair cost, and I want to find the cheapest way to make this country connected again. In this first example, I need to choose some roads. Can I choose two roads? No, there are 4 cities, I cannot connect them just by 2 roads. So probably I need 3 roads. And if I take 3 cheapest roads, then they do the job, they connect all 4 cities. This means the minimum repair cost in this problem is 5, the cost of 3 cheapest roads. Here's another example. There are 7 cities, so to make it connected I need at least 6 roads. Let's try again to choose the cheapest roads. I can take this road of cost 1, all the roads of cost 2, but still I need one more road. Currently I have 2 connected components, the orange one and the blue one, and they're not connected with each other. I can't get from B to D, for example. So I need to connect the blue connected component with the orange one. How do I do this? I can, for example, take this edge of weight 4, of the cost 4. And this would work. This would give me a plan which costs 13. Can I find a cheaper plan? I took 5 cheapest roads and added a road of cost 4. In order to beat me, you have to take 5 cheapest roads and a road of cost 3. But it is easy to see that those combinations don't work. If you take this road of cost 3, it doesn't connect the blue and the orange components. If you take this one, it doesn't connect either. So we found the cheapest way. The cheapest repair plan here costs 13. And here's one more example. Again, I suggest you the following algorithm. Let's just be taking cheapest edges as long as they are useful, as long as they connect some vertices which haven't been connected yet. For example, first I take this edge of cost 1. Now I take this edge of cost 2. Should I take this edge of cost 3? No, it just connects B with C, but they are already connected through the vertex G, so let's not take it. It's useless. Okay, now I can take this edge of cost 3, and this one of cost 3. This one of cost 4, again, it's useless. A and F are already connected through B and G, so I don't take it. I can take this one of cost 4 because it connects D with E, and this one of cost 4, and I'm done. This is a solution, and actually this is the optimal solution. And we will prove later that this algorithm always gives an optimal solution. We saw 3 different though equivalent definitions of trees. First, we say that a graph is a tree if it is a connected graph without cycles. We also say that a graph is a tree if it is a connected graph on n vertices and n-1 edges. And our third definition says that a tree is a graph where there exists a unique simple path between every pair of vertices. Here is an example of a tree. It's quite easy to see that this graph is connected and doesn't have any cycles. So it is a tree according to the first definition. Also, this is a connected graph on 9 vertices and 8 edges, which means it is a tree according to the second definition as well. And for the third definition, we want to show that there exists a unique simple path between every pair of vertices. I won't show it for every pair of vertices, I'll show you for one pair. For example, you want to find all paths between these 2 vertices. There is only one path between them, and it looks like this. And you can check there is a unique simple path between every pair of vertices. Now let's prove that these 3 definitions are actually equivalent. How do we prove such a statement? One way to do it is to prove that the first definition implies the second one, the second definition implies the third one, and then we show that the third one implies the first one. This way we prove that all 3 definitions are equivalent. Why is that? Because if, for example, we want to say that the second definition is equivalent to the third one, we say, look, the second one implies the third one, while the third one implies the first one, which in turn implies the second one. So the second definition implies the third one, and the third one implies the second one, which means they are equivalent. We only need to show these 3 implications. Let's start with the first one. If we have a connected graph without cycles on n vertices, then it must have exactly n-1 edges. We can prove it by induction on n, the number of vertices in the graph. When n is 1, graph has 0 edges, which is exactly n-1. Induction hypothesis says that, say we prove the statement for all graphs with at most k vertices. And in the induction step, we want to prove the statement for all graphs on k plus 1 vertices. Here's how we do it. Start with our graph without cycles and remove some edge. For example, this orange one. I want to say that we have now two connected components. First of all, why don't I have just one connected component? Because if this new graph is connected, say this vertex is connected to this one, then in the original graph, when I had this edge, I did have a cycle. Here it is. But I know that I started with a graph without cycles, a contradiction. Thus, I have at least two connected components. And I actually have at most two connected components because if I add this edge back, I can only decrease the number of connected components by one. So I have exactly two connected components, and none of them has cycles because my original graph didn't have any cycles. Alright, so I remove an edge, I have two smaller graphs connected and without cycles. Since they are smaller, I can apply induction hypothesis to them. If one of them has n1 vertices, the other one has n2 vertices, then I know that the first one, by induction hypothesis, has exactly n1 minus 1 edges, and the second has exactly n2 minus 1 edges. So my original graph has n1 minus 1 plus n2 minus 1 plus 1 removed edge, which is exactly n minus 1 edges, the statement that we wanted to prove. So we proved the first implication. We proved that the first definition implies the second one. Let's prove that the second definition implies the third one. I want to say that if we have a connected graph on n vertices and n minus 1 edges, then there exists a unique simple path between every pair of vertices. First of all, it's clear that there exists at least one path because graph is connected. Assume there are two paths between a pair of vertices. Then these two paths together give me a cycle. And if I have a cycle, then I want to say that I have too many edges. Assume I have a cycle on m vertices and then m edges. I'll be recovering all the edges of my original graph one by one. I know that my original graph is connected, so in order to connect to the cycle each vertex, I have to add at least one edge for each vertex. I have n minus m remaining vertices, so I have to add at least n minus 1 edges, which gives me the total number of at least n edges. But I assume that I started with a graph with n minus 1 edges. This way we get a contradiction. Here's how it works on an example. Assume I have two paths between a pair of vertices. For example, this one and this one. Here's the first path, and here is the second path. From these two paths, I can always extract a cycle, this yellow one. And now I want to recover edges of my original graph. I'll start with the 6 edges of the cycle, and I want to add edges to the 3 remaining vertices. In order to connect each of them, I have to add at least one edge, which means I have at least 9 edges on a graph with 9 vertices. This is too many. I assumed my graph has n minus 1 edges with n vertices. This way we get a contradiction here. So we just proved the first two implications. And the third one is actually trivial. We want to say that if there is a unique path between every pair of vertices, then there are no cycles. Indeed, assume there exists a cycle in my graph. Then the first and last vertices of this cycle have two simple paths between them. Here is one red path and here is the other yellow path. So we prove the third implication as well, which means we finish the proof of equivalence of these three definitions of trees. A spanning tree of a graph G is a subgraph of G, which is a tree and spans all the vertices of G. And a minimum spanning tree is a spanning tree of the smallest weight. Here is an example. That's exactly what we did in the rotor pair problem. This is a tree which spans the whole graph and has the minimum weight. We want to solve this problem each time when we want to connect cities, computers or satellites in a network in an optimal way. This problem has lots of real-life applications, and this is why we know many efficient algorithms for this problem. And we'll see one called Kruskal's algorithm. Actually, we already saw it. This is how it works. It starts with an empty graph and then n-1 times adds an edge which doesn't add any cycle and has the smallest weight. That's exactly what we did in the rotor pair problem. Let me show it to you. First, I add the smallest edge which has weight 1. Then I add the smallest edge which now has weight 2. Now I can't add this edge of weight 3 because it adds a cycle, so I don't add this edge. But I add the other edge of weight 3 because it doesn't create any cycle. Now I can add this edge of weight 3, it doesn't create any cycles, but I don't add this edge of weight 4 because it does create a cycle. So I keep doing this. This edge doesn't create any cycles. I just have 2 connected components in orange, but no cycles. And finally I add this edge. I added n-1 edges. I have a connected graph, a tree, which spans the whole graph. This algorithm is called Kruskal's algorithm, and actually it finds a minimum spanning tree. Let's prove it. We'll show that at every step of our algorithm, the currently added edges belong to some minimum spanning tree. If we prove the statement, then it also means that at the very last step, when we have n-1 edges, this is also a subgraph of some minimum spanning tree. But since minimum spanning tree also has n-1 edges, this means that our tree equals some minimum spanning tree. So our tree is a minimum spanning tree. This way it suffices to prove the statement that at every step the current set of edges is a subset of some minimum spanning tree. We'll prove it by induction on the step number. We call it S. In the very beginning, when we have no edges, clearly empty graph, empty tree is a subgraph of a minimum spanning tree. Induction hypothesis says that we prove the statement for step k, and now we want to extend it to the next step, to the step number k plus 1. We'll show that there exists a minimum spanning tree which contains the first k plus 1 edges chosen by Kruskal's algorithm. And here's how we do it. Assume this is some minimum spanning tree which contains the first k edges chosen by Kruskal's algorithm. You see there is somewhere edge, we'll call them edges e1, e2 through ek. You see it contains edge e1, e2, all other edges, and it contains edge ek-1 and edge ek. Assume it for some reason doesn't contain the next edge, ek plus 1. Then let's add this edge to this graph. Now we have n edges in a graph on n vertices. It's not a tree anymore, which means it contains a cycle. Here is a cycle, and let's find an edge in this cycle which is not chosen by Kruskal's algorithm yet. There must be one edge which does not belong to E1 through Ek, because this set of edges chosen by Kruskal's algorithm never contains a cycle. This means in this cycle there must be a different edge. Let's say this is this edge F. What can we say about the weight of edge F? Since Kruskal algorithm chose edge Ek plus 1 rather than edge Ek, and it always chooses an edge of the smallest weight, it means that the weight of Ek plus 1 is less than or equal to the weight of this edge F. And now we can remove the edge F from the graph and add the edge Ek plus 1. Again, we have a connected graph with n minus 1 edges. We have a tree, and it has at most that weight, which means it's also a minimum spanning tree. So we constructed a minimum spanning tree which contains k plus 1 first edges chosen by Kruskal's algorithm. We just proved the induction step. We just proved that there exists a minimum spanning tree which contains the first k plus 1 edges chosen by Kruskal algorithms. And now induction finishes the proof. In this lesson we will study bipartite graphs. And again we'll start with a problem. Our school has 4 job openings: administrator, programmer, librarian and professor. And there are 4 people who applied for these jobs. Can we fill all the positions? Alice wants to be either an administrator or a librarian. Ben wants to be programmer or librarian. Chris can do administrator or programmer's jobs. And Diana only wants to be a professor. Let us first draw the following graph. It will be a bipartite graph where on the left-hand side we will have 4 vertices corresponding to job openings, and on the right side we will have 4 vertices corresponding to 4 people. A means Alice, B Ben, C Chris, and D Diana. Now I connect a job opening with a person if and only if this person wants to do this job. Here's what it looks like. For example, Alice only wants to be administrator or librarian, so I have 2 edges going from the vertex A. So now we want to find 4 edges in this graph such that they cover all the vertices on the left and they don't share vertices on the right. So we want to find 4 disjoint edges. Clearly only Diana can be a professor, so we'll hire her for this position. Now we want to assign these 3 jobs to those 3 people. Again, this means that we want to find 1 edge going from the administrator position, 1 edge from programmer, 1 edge from librarian, such that they all end at different positions on the right, at different vertices on the right hand side. So we want to find 3 disjoint edges in the remaining graph. We can do this. This is a solution. We found a solution for the original problem. Now let's solve a similar problem. There are 6 students and there are 6 single rooms in a dorm. Can we find a room assignment such that everyone lives in a room he likes? For example, Aaron only likes rooms 1 and 2. Bianca only likes the first 3 rooms. And the remaining preferences you can see on the screen. We want to find such a room assignment that everyone likes her room. Again, let's draw a bipartite graph. On the left side, we have 6 vertices corresponding to 6 people. And on the right side, we have 6 vertices for rooms from 1 to 6. Again, we draw an edge between a person and a room if this person likes the room. For example, Aaron only likes the rooms number 1 and 2, so there are 2 edges going from A. They go to the vertices 1 and 2 on the right side. Can we find such a solution? No. Let's look at Carol, Emma, and Francis. 3 of them like only 2 rooms, rooms number 4 and 5. Since each of these rooms can only fit one person, there is no room assignment which would satisfy Carol, Emma and Francis. This means there is no room assignment for all 6 people either, so there is no ideal solution. Later in this lesson we'll see that actually this is the only situation which can prevent us from finding an ideal assignment. Let me remind you that we defined bipartite graphs as follows. We say that a graph G is bipartite if its vertices can be partitioned into 2 disjoint sets L and R, such that every edge connects a vertex from L to a vertex from R. Or in other words, there are no edges connecting 2 vertices from the same part. And in this case we call L and R the parts of the graph G. Here's an example of bipartite graphs. We colored all vertices of one part red and all vertices of the other part blue. And now you can see that every edge connects a red vertex to a blue vertex. Here is an equivalent definition of bipartite graphs. We can say that a graph is bipartite if and only if it has no cycles of odd length. A bipartite graph can have cycles of even lengths. It can have cycles of lengths 4, 6, 8, but it can never have a cycle of odd length. Let's prove that this definition is equivalent to the original one, to the one that we already know. First, let's prove that if we have a bipartite graph G, with parts L and R, such that every edge goes from L to R, then there are no cycles of odd length. Indeed, when you try to find a cycle in a bipartite graph, each edge takes you to a different part of the graph. So if you want to return to the original vertex to have a cycle, then you have to make an even number of steps. So it can only have cycles of even length, and a bipartite graph never has cycles of odd length. Now let's prove the other direction. Assume we have a graph without odd cycles. We want to prove it's bipartite. We want to construct 2 parts L and R such that all edges go from L to R. If graph is not connected, then we will prove it for every connected component of it, and then we will conclude that the whole graph is bipartite. If every connected component is bipartite, then the whole graph is bipartite too. So we fix some connected component, C1, and we fix a vertex in this component. We color it red. Now for every other vertex of this connected component, we check if there is a path of odd lengths from V to this vertex, then we color it blue. Otherwise, we color it red. And we want to say that this is a good partition, that all edges now go from red to blue vertices. How do we prove it? So let's pick some vertex. Let's pick the vertex V and color it red. Now, if there is a path from V to some other vertex of odd length, we color it blue. And this is a set of blue vertices. For example, there exists a path of length 1 from V to V8, or a path of length 3 from V to V8. That's why we color it blue. And all the remaining vertices we color red. Since this is a connected component, there is a path from V to V3, and we know that there are no paths of odd lengths. So there must be only even length paths from V to V3. So we know that there is a path of even length from V to every red vertex. Now let's prove that this partition is good, that all edges go from blue to red vertices. Assume, towards contradiction, there is an edge between 2 red vertices, for example between V5 and V7. What does it mean? V7 is colored red, which means there is a path of even length from V to V7. Here it is. V5 is also colored red. This means there is a path of even length from V to V5. And now we also add this edge between V5 and V7. We have even plus 1 edge. This is a cycle of odd length. But we know that our graph doesn't have cycles of odd length. We reached a contradiction. Assume again towards contradiction there is an edge between two blue vertices. Then again, there is a path of odd length from V to V1, there is a path of odd length from V to V2, and there is an edge between V1 and V2. Odd plus 1 is odd. So again, we get a cycle of odd lengths, but we know our graph doesn't have such cycles. So this means that all edges go from red vertices to blue vertices. This graph is bipartite. Formally, we say that this partition is good because there are no edges between blue and red vertices. And then we just repeat the same procedure for every single connected component of the graph. If every component is bipartite, the graph is bipartite. A matching in a graph is a set of edges without common vertices. In other words, it's a set of disjoint edges. And the maximal matching in a graph is such a matching that if you add any edge to it, it's no longer a matching. So a maximal matching is a matching which cannot be extended to a larger one by adding new edges to it. And the maximum matching is a matching of the largest size. But in this lesson we will be only interested in matchings in bipartite graphs. Since in a bipartite graph all edges go from one part to the other one, a matching is a set of edges from one part to the other one. And we'll often want to find a matching which covers all the vertices from one part of the bipartite graph. So it will be a set of edges such that they cover all the vertices in one part and connect them to different vertices in the other part. Why would we want to do this? For example, we would like to cover all the job openings by the applicants. This would be a matching. Here's an example. This is a good job assignment and also it's a matching. This is a set of disjoint edges. Or we might want to cover all the students by rooms they like. This would be a matching too. But in this specific case, we know it's impossible. And there is Hall's theorem. Hall's theorem tells us exactly when it is and when it's not possible to cover all the vertices of one side of a bipartite graph by a matching. But in order to understand the statement of Hall's theorem, we first need to define the neighborhood of a set of vertices. If we have a graph G and we select some set of vertices in it, S, then the neighborhood of S, which we denote by n of S, is a set of all vertices connected to at least one vertex in S. All the neighbors of vertices from S. And then Hall's theorem says that in a bipartite graph, which has one part L and the other part R, there is a matching which covers, say, all the vertices from the left part, if and only if the following condition holds. For every subset of vertices on the left, the number of their neighbors on the right is greater than the size of the subset. So Hall's theorem says that if for every subset of the vertices on the left they have more neighbors on the right, then there is a matching which covers all the vertices on the left. And it also says that if there is some subset of vertices on the left which have fewer neighbors on the right, then there is no such a good matching. Here's an example. In this graph, we know that there are three people, Carol, Emma and Francis, which only like 2 rooms. And Hall's theorem says, okay, this is exactly the set S on the left, which has 3 vertices, C, E and F, and they have fewer neighbors on the right. They have only 2 neighbors. This is why there is no such a good matching in this graph. There is no matching in this graph which covers all vertices on the left. Now we'll prove Hall's theorem. Hall's theorem again says that in a bipartite graph there exists a matching which covers all vertices of the left part if and only if the following condition holds. For every subset of the vertices on the left, there are more neighbors on the right. Let's prove the first direction of this theorem. We say if there is a matching, then for every set of vertices on the left, there are more neighbors on the right. Why that? Assume there is a matching which covers all vertices on the left, then for every subset S of the vertices in the left side, we'll just take the matched vertices on the right. There are at least S of them. That's it. Let's see how it works on an example. Say in this graph we have a matching which covers all vertices in the left side. Here it is. It's highlighted in orange. Now for every subset of vertices on the left, for example for these two vertices, I'll just give you two matched vertices on the right. So I have at least that many neighbors. If you ask me to give you at least 3 neighbors for these 3 vertices, yeah, again, I will just give you 3 matched vertices on the right. So we proved one direction of this theorem. If there exists a matching which covers all vertices on the left, then each subset has more neighbors on the right. Now we prove the other direction of Hull's theorem. We know that in our graph, every subset of vertices on the left has more neighbors on the right. And we want to find a matching which covers all the vertices on the left. How do we do this? We'll prove it by induction on the size of L, that is, by induction on the number of vertices in the left part. So I assume that we proved it for all smaller graphs, and now we're proving it for this graph. Let's pick some vertex on the left, and we know that it has at least one neighbor on the right. Okay, so maybe we want to say that this is one edge of our matching. And then we remove these two vertices, have a smaller graph. If there exists a matching in this smaller graph, which covers all vertices on the left, then we're good. We just say we take this matching and our original edge, and altogether this is a matching which covers all the vertices in the left side. We're done. But it's also possible that when we take this vertex on the left and some of its neighbors on the right, we remove these two vertices and there is no matching which covers all the vertices on the left. This is also a possibility. But now we have a smaller graph, and by induction hypothesis we know that if there is no matching which covers all the vertices on the left, it means there exists some subset of vertices which has fewer neighbors on the right. For example, these two vertices on the left have only one neighbor on the right. This is the only reason why we might not have a good matching in the smaller graph. But we know that in our original graph, every pair of vertices had at least two neighbors on the right. This means that these two vertices on the left were connected to the removed vertex on the right. Okay, let's return it to our graph. And now we know that these two vertices are connected to at least two vertices. So we can find a good matching here. We can find a matching which covers these two vertices. Okay, this will be the first part of our final matching. Let's remove these four vertices. And now we want to find a matching on the remaining part of the graph. So we draw again the removed vertex on the left, and we want to find a matching which covers all the remaining vertices on the left. These two. We'll use induction hypothesis again. We have a smaller graph, so we know that if every subset has more neighbors on the right, then there is a matching. This is exactly what we're going to use here. We say, okay, let's fix some subset on the left. And we know that before removing these two vertices on the left, they had at least, altogether all four of them, had at least four neighbors. But now we remove two vertices on the left and two vertices on the right, which means that the remaining two have to have at least two neighbors on the right. We had four vertices with four neighbors, remove two here. So the remaining two vertices must have at least two neighbors now. And that's it. We can use induction hypothesis. We know that this means that there is a matching which covers all the vertices on the left. This is the second part of our final matching. We have this matching and that matching. All together they cover all vertices on the left. We're done. We just saw how this proof works on an example, and now let's give a formal proof. Formally we prove it by induction on the number of vertices on the left side, and the base case is when our graph has only one vertex on the left. Then by this Hall's condition it has at least one neighbor on the right, so there is a matching of size 1. Induction hypothesis says that we proved it for all graphs with at most k vertices on the left. And induction step is to prove it for all graphs with k plus 1 vertices on the left. How do we do this? We pick some vertex on the left and it has some neighbor on the right. We fix them, try to remove them. If there is a matching which covers all the remaining vertices on the left, then we're done. We take this matching at this edge and we have a good matching for the original graph. But we also saw that it's possible that there is no such a good matching on the remaining part of the graph. But then, by induction hypothesis, it means that there exists some subset S1 of the vertices on the left, which has fewer neighbors on the right. Now we return that removed right vertex, and we know that this subset S1 has exactly S1 neighbors on the right. And Hall's condition also holds for all smaller sets here. So by induction hypothesis, there is a matching between this subset S1 and the corresponding subset T1 on the right. We take this matching and remove those vertices from the graph. Now again, by Hall's condition and induction hypothesis, there is a matching on the remaining part of the graph, which covers all the remaining vertices on the left. We combine these two matchings and get a matching which covers all vertices in the left side. In this lesson we'll study properties of planar graphs. But first, the following problem. 4 subway stations, can you connect every pair of them such that subway lines don't cross? Let's try to do it. First, I can draw a cycle on these 4 stations. Now I can connect this pair and I want to connect the remaining pair. I can't just draw this diagonal, it does cross the other diagonal. But I can connect them in a different way, for example like this. So I just connected all 4 stations without any subway line crossings. Can you do the same thing for 5 subway stations? Let's try. Again, I can first draw a cycle. Now I can connect the left bottom station to all the other stations. I can connect the bottom one to other stations as well. And there is one remaining pair which I want to connect. I can't connect it directly, it does cross some other subway line. I can't connect it this way, and I can't connect it this way. And actually, it's impossible to connect 5 subway stations such that no pair of subway lines cross each other. We'll prove it later in this lesson. When we lay a circuit on a computer chip, we usually don't want the wires to cross. If the wires don't cross, then we can make it a single layer circuit, which is much cheaper to produce. And this is exactly the idea behind planar graphs. Or another popular example is the famous 3 utilities problem. We have 3 houses and 3 utilities: water, power, and gas. And we want to connect every house to every utility. And we don't want the connections to cross. For example, in this drawing, these 2 connections do cross. And actually, it's impossible to connect 3 houses to 3 utilities without any crossing connections. We'll prove it soon. A graph is called planar if it can be drawn in the plane such that no edges meet except obviously at their endpoints. And even if you usually draw a graph with intersecting edges, it still might be planar if it can be drawn without crossing edges. For example, this graph is planar because it can be drawn without crossing edges. For the same reason, this graph is planar. There are no crossing edges here. And actually, this graph is planar too, because we can draw it without crossing edges, like this. This graph is not planar because whichever way you draw it, you will always have a crossing pair of edges. We'll prove it soon. There is also interesting connection between maps and planar graphs. Here is a map of South America. Now I will draw a vertex somewhere in the middle of each country. And I will connect two countries if they have a common border, if they are neighbors. For example, I will connect Chile to Peru, Bolivia and Argentina, because those three countries are neighbors of Chile. I will add all edges to this graph, between all pairs of neighbors. And this graph is planar. You see, there are no crossing edges. And this connection works in the other direction as well. If I have some planar graph, I can always draw some countries around each vertex in such a way that in the planar graph only the neighboring countries are connected. So maps are basically equivalent to planar graphs. With a few minor exceptions, we will always assume that every country is continuous, and we will also assume that there are no bizarre countries with infinite perimeters. Otherwise, maps are equivalent to planar graphs. Now we will prove the most famous result about planar graphs, Euler's formula. Let us draw a planar graph on the plane. And now we say that a face of this drawing of a graph is a region bounded by the edges of the graph. And note that there is always one infinitely large face, which we call the outer face. Here's an example. This is a planar graph drawn without any crossing edges, and this is one of its faces. Here's another one, third one, fourth one, fifth one, and there is also an infinitely large outer face, number 6. Euler's formula says that if we have a connected planar graph drawn in the plane without crossing edges, then the number of vertices minus the number of edges plus the number of faces is always equal to 2. In this example, we have 5 vertices, we have 9 edges, and we already know that we have 6 faces. So 5 minus 9 plus 6 is exactly 2. Euler's formula works for this graph. Now let's prove it in general. We'll prove it by induction on the number C of cycles in graph G. The base case is when our graph doesn't have any cycles, when C equals 0. But we know that a connected graph without cycles is a tree, and tree has only one infinitely large face. We also know that a tree on V vertices has V minus 1 edges. So Euler's formula for a tree says that V minus E plus F, which in the case of a tree is V minus 1 plus 1, is 2. Euler's formula works for trees. It works in the base case. Our induction hypothesis is that the formula works for all graphs with at most C cycles. And in the induction step, we'll prove that it works for all graphs with C plus 1 cycles. How do we prove it? Let's fix a graph with C plus 1 cycles. Now we choose an edge which belongs to some cycle and we remove it. This merges two faces of our graph. So in the new graph we have fewer cycles because we just removed one edge from a cycle, we just eliminate at least one cycle. we have one fewer faces and we also have one fewer edges, while we have the same number of vertices. We didn't touch vertices at all. Since we have fewer cycles, we can use induction hypothesis, which says that Euler's formula works for this new graph. But then Euler's formula also works for our original graph, because the new graph has one fewer edges and one fewer faces. So v minus e plus f is v1 minus e1 plus 1 plus phi1 plus 1, which is 2. We just proved Euler's formula. Here how this proof works on an example. This graph has several cycles. For example, it has this cycle of length 3. Let's pick some edge from this cycle, for example this one, and remove it. Our new graph has one fewer edges and the same number of vertices. And also we just merge two faces, 6 and 1. So the new graph has one fewer faces. And since by induction hypothesis Euler's formula works for this new graph, it also works for the original graph. Now we'll see what Euler's formula gives us. First, I want to say that every face has at least 3 edges. For example, this face has 5 edges, this face has 3 edges, and this face has 4 edges. And there is no way to draw a face with 2 or 1 edges. And also, every edge belongs either to 2 or 1 faces. For example, this edge belongs to 2 faces. This edge belongs to 2 faces. But this one belongs only to 1 face. Every edge belongs either to 1 or 2 faces. What can we conclude from this? Let's consider a planar graph on at least 3 vertices. And we know that each face has at least 3 edges. We also know that each edge belongs to at most 2 faces. Now let's count the number of pairs of a face and an edge such that this edge belongs to this face. First, we know that the number of such pairs is at least 3 times the number of faces, because each face has at least 3 edges. On the other hand, we know that the number of such pairs is at most 2 times the number of edges, because each edge belongs to at most 2 faces. This gives us that f, the number of faces, in a planar graph is at most 2e over 3, where e is the number of edges. Recall Euler's formula, v minus e plus f equals 2. And now we also know that f is at most 2e over 3. I want to say that this gives us the following. Every connected planar graph on at least 3 vertices has at most 3v minus 6 edges. That's how we prove it. From Euler's formula we know that 2 equals v minus e plus f, which is, we now know, is upper bounded by v minus e plus 2e over 3, which is v minus e over 3. Now we multiply this inequality by 3 and we get that the number of edges e is at most 3v minus 6. Also, we can conclude that every connected planar graph has a vertex of degree at most 5. Because if that wasn't the case, if there was a planar graph where a degree of each vertex is at least 6, then the number of edges in such a graph would be the sum of the degrees divided by 2, which is at least 3v. But we know that e must be at most 3v minus 6, a contradiction. So now we know that every planar graph has a vertex of degree at most 5. And we also know that in a planar connected graph on at least 3 vertices, the number of edges is at most 3v minus 6. Now we can say that the complete graph on 5 vertices is not planar. That is, we cannot connect 5 subway stations without crossing subway lines. This is why. We have 5 vertices and 10 edges in the complete graph on 5 vertices. But in a planar graph with 10 edges, we would have 3v minus 6 greater than 10. But in the full graph, in the complete graph on 5 vertices, 3v minus 6 is 9, which is less than 10. So this graph is not planar. There is no way to draw the complete graph on 5 vertices without crossing edges. But do you think we can connect 3 houses with 3 utilities without crossing connections? Do you think the complete bipartite graph on 3 and 3 vertices is planar? We know that in this graph we have 6 vertices and 9 edges. And this does satisfy the inequality E is at most 3v minus 6. So we can't yet conclude that this graph is not planar. Let's see what we can say about bipartite planar graphs. We already know that bipartite graphs don't have cycles of odd length, which means they can have a face on 3 edges. So every face in a bipartite planar graph has at least 4 edges. And now, if again we compute the number of pairs, edge and a face, such that this edge belongs to the face, then we would say that the number of pairs is at least 4 times the number of faces, and again it's at most 2 times the number of edges, because each edge belongs to either 1 or 2 faces. From this we conclude that in a bipartite planar graph, f is at most e over 2. Now from Euler's formula v minus e plus f equals 2, and this recent observation f is at most e over 2, we conclude that in a bipartite graph on at least 4 vertices, in a bipartite connected planar graph on at least 4 vertices, e is at most 2v minus 4. That's how we show it. 2 is v minus e plus f by Euler's formula, which in a connected bipartite planar graph is at most v minus e plus e over 2. That is v minus e over 2. We multiply it by 2 and we get that the number of edges is at most 2 times number of vertices minus 4. Now let's look at this complete bipartite graph on 3 and 3 vertices. It has 6 vertices, 9 edges. So the number of edges, 9, is not less than or equal to 2v minus 4, which is 8. So this graph is not bipartite. There is no way to draw it in the plane without crossing edges. Hi everyone! In this lesson we will be coloring graphs, and we will start with a special case of map coloring. Assume that I give you the map of continental South America and I ask you to color it using as few colors as possible, such that no pair of neighboring countries share a color. This is what we typically see in political maps. Neighboring countries are assigned different colors. So let us first note that Brazil, Bolivia, Paraguay and Argentina are all neighboring each other, which means they all must be assigned different colors. So we have to have at least 4 colors. And if we can find a good coloring which uses only 4 colors, then that's it. The answer to the problem is 4 colors is the minimum number. Let us try to find such a coloring. First we can color Uruguay either with red or green, it doesn't matter because all of its neighbors have already been colored. Now let's say we colored Chile with blue, and then maybe we use red for Peru and blue for Ecuador, then green for Colombia, and the remaining countries then can be just colored using red and green. We did find a coloring which uses only 4 colors. Let us try to solve the same problem on the map of the land of Oz from the wonderful Wizard of Oz. Again, there are 3 countries which are neighboring each other, so the number of colors is at least 3. And we will try to find a coloring which uses only 3 colors. We can color the interior part of the map using only 3 colors, red, green and blue. Now we can color the desert with red, and then the remaining part can easily be colored with green and blue. So here the minimal number of colors is just 3. And the last problem is to color cantons of Switzerland, such that again, no pair of neighboring cantons share a color. We can find 4 cantons which are neighboring each other, so the number of colors is again at least 4, and there exists a valid 4 coloring of this map. Let us summarize what we did. We colored the map of South America with 4 colors, we colored the land of Oz with 3 colors, and we also colored Switzerland with 4 colors. We never used more than 4 colors. And actually, this is a law of nature. Appel and Haeckel in 1976 proved that every map can be colored using at most 4 colors. Here the word map comes with an asterisk. We actually assume that all countries are continuous, and we also don't consider bizarre countries like which have infinite perimeter. But otherwise, this is a theorem. Yeah, every map can be colored with only 4 colors. What is very interesting and almost unique about the proof of this theorem is that it uses computer search. Originally, in 1976, Appel and Haeckel said that if there exists a counterexample of this theorem, then it must be one of these 2000 graphs. And they used computer search to find 4 coloring for each of them. Back in the 70s, it took more than 1,000 hours of computer time. Later, Robertson, Sanders, Seymour and Thomas gave a much simpler proof of the same result, but it still uses computer search. We've seen map colorings, and now we will define and see a couple of examples of graph colorings. A graph coloring is a coloring of graph vertices such that no pair of adjacent vertices share the same color. And the chromatic number of a graph G, denoted by chi of G, is the minimum number of colors needed to color the graph G. Let us see an example. Say I first wanna only color the 5 external vertices of this graph. I can easily color 4 of them using only 2 colors. But now I cannot color the 5th external vertex in red nor in blue, so I have to introduce a third color. And once I introduce the third color, I can easily finish the coloring. So the chromatic number of this graph must be at least 3, and since there is a valid coloring which uses only 3 colors, the chromatic number of this graph is exactly 3. What about full graphs? In a full graph, every pair of vertices is connected by an edge, which means that no pair of vertices can share the same color. So every vertex must have its own color. Thus, the chromatic number of a full graph on n vertices is exactly n. Let us consider path graphs. Clearly, I cannot color all vertices of a path graph the same color, so I have to use at least 2 colors. And I can easily color it using 2 colors. Say I color all odd vertices in red and all even vertices in blue. This is a valid coloring. So the chromatic number of a path graph is always 2. What about cycles? If a cycle has even length, then I can use the same strategy. Indeed, if I color all odd vertices red and all even vertices blue, then every edge will connect a red vertex and a blue vertex. So the chromatic number of a cycle of even length is exactly 2. But if my cycle has odd length, then I can't use the same strategy. By the time I color the last vertex, I'll see that I can't color it neither red nor blue. So I have to introduce the third color again. And the chromatic number of a cycle of odd length is 3. Now let's look at bipartite graphs. Actually, this can be considered as a definition of bipartite graph. Every bipartite graph can be 2-colored. And on the other hand, if a graph can be colored in 2 colors, then it is bipartite. Indeed, bipartite graph is a graph where all vertices go from one part to the other part. So let me color all vertices of one part red and all vertices of the other part blue. Then all edges will connect a red and a blue vertex. We will see that some graph classes can be colored in a few colors. First, the theorem by Appel and Huggins says that every map can be colored in at most 4 colors. And when we were studying planar graphs, we saw that every map corresponds to a planar graph and every planar graph corresponds to a map. So actually, Appel's Huggins theorem says that every planar graph can be colored in at most 4 colors. This theorem is very hard to prove. It uses sophisticated proof techniques and also computer search, so we won't prove it in our course. But we will prove a weaker version of this theorem. Right now we'll show that every planar graph can be colored using at most 6 colors. We'll prove it by induction on n, the number of vertices in our planar graph. As always in a proof, by induction we want to have some base case. Here we'll say that if our graph has at most 6 vertices, then it clearly can be colored in at most 6 colors. Indeed, every vertex can be assigned its own color. Induction assumption says that every planar graph on k vertices can be colored in at most 6 colors. And then induction step is every planar graph on k plus 1 vertices can be colored using at most 6 colors. We want to prove induction step. I want you first to recall a lemma which we proved when we were studying planar graphs. For planar graphs we proved Euler's formula, and from it we concluded that every planar graph has a vertex of degree at most 5. Now, assume we have a planar graph on k plus 1 vertices. It must have a vertex of degree at most 5. Let's call it V. Now let's try to color the remaining part of the graph, everything except for vertex V. This part contains k vertices, and by induction assumption we can color it using at most 6 colors. And now we want to find a color for V. But since V has only 5 neighbors, we can always find 1 out of 6 colors for V, which finishes our coloring of a planar graph on k plus 1 vertices. And by induction, this finishes the proof. We show that every planar graph can be colored in at most 6 colors. Actually, using similar ideas, you can prove that every planar graph can be colored in 5 colors. Let's now color graphs of bounded degree. Let's say G is a graph of degree delta, which means that each of its vertices has degree at most delta. Then we'll show that G can be colored in delta plus 1 colors. We'll be coloring vertices of G one by one, and when we want to color some vertex V, we look at the colors assigned to its neighbors. There are at most delta of them, so we can always choose 1 out of delta plus 1 colors for V, which means we can always find a color for every vertex of G. So G can be colored in delta plus 1 colors. In fact, there is a stronger version of this theorem proved by Brooks, which says that a graph of maximum degree delta can be colored in delta colors except for 2 cases: when this graph is a full graph or when it is a cycle of odd length. It's time to see some applications of graph colorings. Here's the first one. Say some students take different exams, and there is just one exam for every course, which means that all students who take course A must take an exam on this course the same day. And no student can take 2 exams the same day. What is the minimum number of days needed to schedule all the exams? Here's how we can solve the problem. Let's construct a graph where each vertex will correspond to a course. And we'll draw an edge between 2 vertices if there is a student who takes both of these courses. So if there exists a student who takes both the course on graphs and the course on proofs, we draw an edge between proofs and graphs. Now, if we color this graph, then we get a schedule of the exams. For example, all red exams can be scheduled the same day. Indeed, they color the same color, which means there are no edges between them. So there are no students who takes any pair of this exam. So we can easily schedule these red exams the same day. Same with the blue exams, we can schedule them the same day, and the green one. So we need 3 days, and here is how we can schedule the exams. In the bandwidth allocation problem, we want to assign radio frequencies to different stations, and roughly speaking, two stations are allowed to use the same frequency if they are far apart. What is an optimal assignment of frequencies to different stations? Again, we can construct a graph where each vertex corresponds to a radio station. And we will connect a pair of stations by an edge if they are close enough, if they are not allowed to use the same frequency. Now let's color this graph. I want to say that all vertices of the same color can be assigned the same radio frequency. Indeed, for example, all blue vertices can be assigned the same frequency, because by the definition of graph coloring there are no edges between blue vertices, which means every pair of these stations is far apart, so they all can reuse the same radio frequency. And the chromatic number of this graph is the minimum number of radio frequencies which we need for the given stations. Graph colorings have many more applications, including scheduling problems such as assigning aircrafts to flights, including the register allocation problem, which is a way to speed up computations by caching frequently used variables. The Sudoku puzzle is basically the problem of coloring a graph in 9 colors. It has also many applications in taxi scheduling and many other problems. In this lesson we will be studying graph cliques and independent sets. Let me start with the following problem. I give you a friendship graph where each vertex corresponds to a person and there is an edge between two people if they are friends. And I ask you to find the largest clique in this graph. And the clique is a set of people which all know each other. It's quite easy to find a clique of size 3 in this graph. 3 people which know each other. Is there a larger clique in this graph? First of all, if we want to find a larger clique, then we can ignore vertices of degree less than 3. Indeed, if we only want to find a clique of size 4 or 5 or even larger, then every vertex in this clique must have degree at least 3. So we can safely remove vertices of degree 0, 1 and 2. Now we have only 5 vertices. Can we have a clique of size 5? No, because there are 2 people which don't know each other. The blue one doesn't know the green one. So the largest clique in this graph is of size 3 or 4. Let's try to find a clique of size 4. Between blue and green one, we have to choose at most one. Let's say I want to take the green one. And then I can take these 3 people, which all together form a clique of size 4. So the largest clique in this graph has size 4. Now I know that the largest clique in this graph is of size 4. And I'm asking what's the largest set of strangers in this graph? What's the largest set of people such that no 2 of them know each other? First of all, I can only take at most 1 person from the clique, because if I take 2 of them, they will know each other. This is a clique. Okay, so I can only take at most 1 of them from the clique, but how many can I take out of the clique? Can I take all 4 of them? No, because the blue one and the orange one know each other. So I can only take at most 3 people out of the clique and at most 1 from the clique. So the largest set of strangers is of size at most 4. Can I find a set of strangers of size 4? Yes, I can. I can take these 3 people out of the clique, they don't know each other, and I can also add this person from the clique. These 4 people are strangers. So this is the largest group of strangers in the given graph. Here is another interesting problem. Recall that the complement of a graph is a graph which contains an edge if and only if the original graph doesn't contain this edge. For example, the complement of this empty graph is a full graph. I ask you to construct a graph such that in its complement there are 4 vertices without any edges between them. It's easy to construct one of these graphs. We just draw all edges between some 4 vertices of the original graph. Then, by the definition of the complement graph, there are no edges between these 4 vertices in its complement. And you can add more edges in the original graph. It doesn't change the fact that you have 4 vertices with all edges between them. So in the complement you have 4 vertices without edges between them. As you already know, a clique in a graph is a set of vertices such that they all are connected to each other. And the maximal clique is a clique which cannot be extended to a larger clique. Formally, it's a clique which is not contained in any other clique. And the maximum clique is a clique of the largest size. And the last piece of notation is the clique number of a graph G, which we denote by little omega of G, is the size of a maximum clique in G. Let us see some examples. In this graph, these 3 vertices form a clique of size 3. We also call it a triangle. But this clique is not a maximal clique because it can be extended to a clique of size 4. This clique of size 3 is a maximal clique because there is no way to extend it to a larger clique. And this clique of size 4 is a maximum clique because this graph doesn't contain larger cliques. It doesn't contain cliques of size 5. Similarly, we can define independent sets. An independent set in a graph is a set of vertices such that there are no edges between them. A maximal independent set is an independent set which cannot be extended to a larger one. And again, a maximum independent set is an independent set of the largest size. And the independence number of a graph G, denoted by alpha of G, is the size of a maximum independent set. Now let's see some examples. Here is an independent set of size 2. And this set is not a maximal independent set because it can actually be extended to an independent set of size 3. Here is an independent set of size 3 and it is a maximal independent set because there is no way to extend it to an independent set of size 4. And this is a maximum independent set. This is an independent set of size 4, which is the largest one in this specific graph. So the independence number of this graph is 4. We already saw a connection between cliques in a graph and independent sets in its complement. Let's just state it one more time formally. If there is a clique in a graph, then there are all edges between those vertices. Then in the complement of this graph, there would be no edges, so those vertices would form an independent set. Cliques in a graph correspond to independent sets in its complement. And the largest clique, a maximum clique, would correspond to the largest or a maximum independent set in its complement. So the clique number of a graph equals the independence number of its complement. Or in our new notation, little omega of G equals alpha of the complement of G. Do you already see a connection between graph colorings and independent sets? Here it is. Let's look at this graph and one of its colorings. By the definition of graph coloring, there are no edges between vertices of the same color. So each color forms an independent set. In this example, there are no edges between vertices of the red color, no edges between vertices of the blue color, and no edges between vertices of the green color. Each color forms an independent set. And using this observation, we can prove the following theorem. For every graph G, the product of its chromatic number and its independence number is greater than or equal to n. Let's prove this theorem. First, we know that all n vertices can be partitioned in chi of g groups. Each of them is just a group of the same of vertices of the same color. So there are chi of g groups, and each of them forms an independent set. We also know that each independent set in a graph has size at most alpha of g, because alpha of g, by definition, is the largest size of independent set. And this implies that n, the number of vertices, is less than or equal to chi of g times alpha of g. Now we'll prove Mantle's theorem. Recall that a triangle is a clique of size 3. Mantle's theorem says that a graph on n vertices without triangles can only have at most floor of n squared over 4 edges. We will prove this theorem again by induction on n, the number of vertices in our graph. And we will consider two base cases, n equals 1 and n equals 2. When n equals 1, graph can contain only 0 edges, because there is only one vertex. And actually the floor of n squared over 4 in this case is a floor of 1/4 is 0, 2. When n equals 2, then a graph on two vertices can contain at most one edge. And the floor of n squared over 4 is exactly 1. So both base cases hold. An induction assumption, induction hypothesis will be that the statement of theorem holds for all graphs on at most k minus 2 vertices. And the induction step would be to show that the statement also holds for all graphs on at most k vertices. Note that the step of the induction in this case is of size 2, and this is exactly why we consider two base cases. We proved it for graphs of size 1, we proved it for graphs of size 2, and then induction step of size 2 will carry on the statement for all integers. Now we'll prove induction step. Let us pick two connected vertices, u and v. We want to say that the sum of the degree of u and degree of v is at most n. Indeed, assume it's greater than n. Then by the pigeonhole principle, there exists some vertex x such that both u and v are connected to x, which forms a triangle. But we know that our graph doesn't contain any triangles. So the degree of u plus the degree of v must be at most n. Now let's remove u and v from our graph and let's denote the remaining graph by h. H now has only k minus 2 vertices. So we can apply induction hypothesis to the graph H. So by the induction hypothesis, the number of edges in the graph H is at most the floor of n minus 2 squared over 4. Let's now count the number of edges in G. It has all edges from H and also edges going from the vertices u and v. We know that sum of their degrees is at most n, but these two degrees count the edge between u and v twice. So the actual number of edges that u and v have is at most n minus 1. So the number of edges in G is upper bounded by the number of edges in H plus n minus 1. Now we just simplify the expression n minus 2 squared. We know it's n squared minus 4n plus 4. And when you divide minus 4n plus 4 by 4, you get the following expression. Floor of n squared over 4 minus n minus 1 plus n minus 1, which equals floor of n squared over 4, exactly what we wanted to prove. There is a generalization of Mantle's theorem which is called Thurin's theorem. Mantle's theorem says that if a graph doesn't contain cliques of size 3, then there are a few edges. Thurin's theorem says that if a graph doesn't contain cliques of size r plus 1, then there are somewhat few edges. For example, if you take R to be 2 in Thuram's theorem, you will get exactly the statement of Mantle's theorem. And in fact, both theorems are tied, which means that there are graphs which have exactly this number of edges. For Mantle's theorem, this would be a complete bipartite graph where the left part has n over 2 vertices, the right part has n over 2 vertices, and the graph has all edges between these two parts. This would be n squared over 4 edges, exactly the number from Mantle's theorem. For Thuram's theorem, there is a more general tight example, which is called a Thuram graph. You just partition all the vertices of the graph more or less evenly in R parts and connect all pairs of vertices from different parts. In this lesson, we will be studying Ramsey theory, which is my absolutely favorite part of discrete math. Ramsey theory says that in every large enough system, there exists a subsystem with extremely nice structure. This theory was first observed by Frank Ramsey and was later developed by Paul Erdős and many other great mathematicians. But let us start with the following simple problem. Can you construct a graph on 5 vertices such that it doesn't contain a clique of size 3 nor an independent set of size 3? Yes, it's easy. There are many correct solutions and one of them is a cycle of length 5. We know that the clique number of a cycle is 2 and the independence number of the cycle of length 5 is also 2. So there are no cliques of size 3, no independent sets of size 3 in this graph. And now, can you construct a graph of size 6 which doesn't contain cliques of size 3 nor independent sets of size 3? No, it's impossible, and we will prove it. First, let's fix some vertex of this graph. Let's call it V. Since there are 5 other vertices, V must be either connected to at least 3 of them or must be disconnected from at least 3 of them. Let us consider the first case. V is connected to 3 vertices. Let's call them V1, V2 and V3. If there exists at least one edge between these 3 vertices, say V1 is connected to V3, then we have a 3 clique, V, V1 and V3. But if there are no edges between these 3 vertices, then we have an independent set of size 3, which is formed by V1, V2 and V3. So I just showed that in one case, there exists a clique of size 3. In the other case, there exists an independent set of size 3. We showed it for the case when V is connected to at least 3 vertices. In the other case, one can show using absolutely the same argument that, again, there either exists a clique of size 3 or an independent set of size 3. So we now can say that in every graph of size at least 6, there either exists a clique of size 3 or an independent set of size 3. And this is exactly the kind of structure which Ramsey theory studies. There is an interesting story about Ramsey numbers. In the 1950s, the Hungarian sociologist Zsalai was studying friendship between children. And he observed that in any group of 20 children, there is a group of 4 children which are either all friends or not friends. So he checked many groups of 20 children and he observed that he can always find a group of 4 children such that they all are friends or there is no pair of friends between them. Luckily, he knew the famous Hungarian mathematicians Erdős, Thuram and Sós, who are very well known in Ramsey theory. And they said that actually this is a simple result in Ramsey theory, which says that, yeah, in every group of 18 or more people, you can find either a 4 clique or an independent set of size 4, which in the language of friendship graphs means that there is a group of size 4 which are all friends or which are not friends. Well, it's time to formally define Ramsey numbers. So for 2 integers k and l, the Ramsey number R of k and l is the minimum number such that every graph with at least that many vertices must either contain a clique of size k or an independent set of size l. So every graph with at least that many vertices must have either one or the other. For example, we know that R of 3 is 6. Indeed, we saw a graph on 5 vertices which doesn't contain a clique nor an independent set of size 3. But we just proved that every graph on 6 vertices must contain either of them. It is also known that R of 4 and 4 is 18, which is exactly the reason why in every group of 18 and more people there are either 4 friends or 4 strangers. But even R55 is not known. We know that it's at least 43 and it's at most 48. And it's a big open problem in mathematics to find the exact value of R5 and 5. How do we know that Ramsey numbers exist? How we know that for every values of k and l there exists a Ramsey number of k and l? This would mean that whatever values for k and l you pick, large enough graphs always contain either a large clique or a large independent set. Well, we know that for small values of k and l, the Ramsey numbers do exist. For example, if k and l are both at most 3, then yes, Ramsey numbers do exist, we will know them. And later, we will prove that R of k and l is less than or equal to R of k minus 1 and l plus R of k and l minus 1, which gives us an upper bound on the Ramsey number for all values of k and l, which means that for every value of k and for every value of l, there exists a Ramsey number R of k and l, which means whatever values you fix for k and l, large enough graphs will always contain either a clique of size k or an independent set of size l. Let us now prove this inequality. This is the main theorem in Ramsey theory. So we want to prove that R of k and l is less than or equal to than R of k minus 1 and l plus R of k and l minus 1. How do we do this? Consider a graph G on that many vertices. And we'll just show that it either contains a clique of size k or an independent set of size l. In order to do so, we fix some vertex v. And let A denote the set of neighbors of v, and B denote the remaining vertices. So V is connected to all vertices in A and is not connected to any vertex in B. Now we know that the total number of vertices in this graph is the size of A plus the size of B plus 1. We want to count the vertex V itself. And on the other hand, the number of vertices in this graph is R of k minus 1 and l plus R of k and l minus 1. From this, we can conclude that either A is greater than R of k minus 1 and l, or B is greater than R of k and l minus 1. Indeed, assume not. Assume both of them are less. Then their sum plus 1 will be smaller than R of k minus 1 and l plus R of k and l minus 1. So at least one of these inequalities must hold. Let us now assume that the first inequality holds, namely that A is greater than or equal to R of k minus 1 and l. By the definition of this Ramsey number, it means that either this subgraph on A vertices contains an independent set of size L, in which case we are done, because it means that our original graph contains an independent set of size L. This is exactly what we want to prove. Or maybe this graph on A only contains a clique of size k minus 1. But this case is also good for us, because now we can add V to these vertices from A, and since V is connected to all vertices from A, they all together form a clique of size k, which is again exactly what we want to prove. So in one case we show that there exists a large independent set, in the other case we show that there exists a large clique. This was the first case. The second case is when B is greater than or equal to R of k and l minus 1. And again, by the definition of the Ramsey number, this means that either B has a k clique, which is good for us, we're done. Our original graph has k clique. Or maybe B contains an independent set of size only L minus 1. But now again, we join this set B with our vertex V. Since B is not connected to anything in B, they altogether form an independent set of size L. Exactly what we wanted to find. Now let's see how this proof works on an example. Let me draw all the neighbors of the vertex V on the left and all the vertices which are not connected to V on the right. So on the left I have this part of the graph which I called A in the proof, and on the right I have this part of the graph which I called B in the proof. And there are two cases. Either A is greater than R of k minus 1 and L, or B is greater than R of k L minus 1. Consider the first case. By the definition of this Ramsey number, k minus 1, L, either A contains an independent set of size L, which means our graph contains an independent set of size L and we're done, or A contains a clique of size k minus 1. But then we can add this vertex V to the clique and we'll have a clique of size k, which is good, which is exactly what we wanted to find. In the other case, if B is large, then again, either B contains a k clique, which is good for us, or B contains an independent set of size L minus 1. And then we can add the vertex V to it and get an independent set of size L. In this lesson we will study vertex covers, which, as you will see, is an extremely natural notion. But as always, we will start with a simple problem. We want to install the antivirus system on as few computers as possible, such that it covers all the network connections between computers. In the graph language, this means that we want to choose as few vertices as possible, such that they cover all the edges of the given graph. We see in this graph there are 12 edges, and the maximum degree of a vertex is 4. So we can hope that there are 3 vertices of degree 4 each, such that they altogether cover all 12 edges. But if we take all the vertices of degree 4, we see that they don't cover the central network connections. So there is no solution which uses only 3 computers. We have to take at least 4 computers. And this is easy to achieve. We just add the central computer. And now we cover all the network connections. Alright, let's see a different example. This network. Here the number of edges is 9 and the maximal degree of a vertex is 3. So we could hope that there are 3 computers of degree 3 each, which cover all the 9 connections. But now it's easy to check that whatever triple of computers you choose, they don't cover all network connections. Here we show it for 1 triple of computers. You can check it for the others. But with 4 computers, it's easy to cover all the network connections. Here's an example. In the third network, it's also easy to show that we have to use at least 6 computers, and there is a solution which takes only 6 computers. For example, these 6 ones. A vertex cover of a graph is a set of vertices such that they cover all edges of the graph. In other words, a vertex cover of G is a set of vertices C such that every edge in G is connected to some vertex in C. Every edge is incident to at least one vertex in C. A minimal vertex cover is a vertex cover which does not contain any smaller vertex cover. It's a vertex cover such that you cannot remove any vertex from it. If you remove anything, it's not a vertex cover anymore. And a minimum vertex cover is a vertex cover of the smallest size, such that this graph doesn't have smaller vertex covers. And we denote the size of the minimum vertex cover in a graph by bet of G. Let's see some examples. Here's some graph, and this is a vertex cover, because every edge of this graph is connected to at least one blue vertex. This vertex cover is not minimal, because if we remove this vertex with an orange edge, it's still a vertex cover. We still cover all edges of this graph. So this vertex cover is not minimal. Okay, let's also look, this is some vertex cover though. Let's look at the remaining vertices, which don't belong to this vertex cover. These two orange vertices. If there was an edge between them, then this edge wouldn't be covered by our vertex cover, so it wouldn't be a vertex cover. This means that if you take some vertex cover and consider all vertices which don't belong to it, they form an independent set. There are no edges between them, because every edge must be covered by at least one vertex of vertex cover. So all vertices which don't belong to some vertex cover form an independent set. Here's an example of minimal vertex cover. Here, if you remove at least one vertex, it's not a vertex cover anymore. So this is a minimal vertex cover. And this is a minimum vertex cover, because there are no vertex covers of size 3 in this graph. Again, if we consider the remaining vertices, they form an independent set. And if we had a minimum vertex cover, then the remaining vertices would form a maximum independent set. So we already see that a set of vertices is a vertex cover if and only if its complement forms an independent set. And from this we can get this formula: beta of g plus alpha of g equals n. The size of the largest independent set plus the size of the minimum vertex cover is always n, the number of vertices in the graph. In this video we'll prove very beautiful Koenig's theorem. Let me first remind you what a maximal matching is. A matching in a graph is a set of disjoint edges, that is, edges which don't share vertices. And a maximal matching is a matching where we can't add any edge, such that if we add an edge, it's not a matching anymore. It is possible to show that if we take all the vertices of some maximal matching, you get a vertex cover. This is not necessarily minimum vertex cover, this is some vertex cover. Why is that? Because assume the set of vertices don't cover some edge from u to v. Then we can add this edge to a matching. So our original matching wasn't maximal, contradiction. But there is even nicer connection between maximum matchings and minimum vertex covers in bipartite graphs. This is called Koenig's theorem. Koenig's theorem says that in every bipartite graph, the number of edges in a maximum matching equals the number of vertices in a minimum vertex cover. Let's prove it. Given a graph G, given a bipartite graph G, where we call one part L and the other part R, we have some maximum matching. We'll show that the minimum vertex cover has the same number of vertices as the number of edges in this maximum matching. First, we'll show that every vertex cover must contain at least one vertex from each edge of a matching. Consider this bipartite graph. This is a matching in it. These three edges are disjoint, so this is a matching. And in fact, this is a maximal matching too. In order to cover the first edge from this matching, we have to take at least one of its vertices. In order to cover the second edge from this matching, we have to take, again, one of its endpoints. And same with the third edge. So we have to take, in every vertex cover, we have to take one vertex for each edge in the matching. So the number of vertices in a minimum vertex cover is at least the number of edges in a maximum matching. And now we will prove the other direction. Then the number of vertices in a minimum vertex cover is upper bounded by the number of edges in a maximum matching. Once we prove this, we prove the theorem, because we prove both inequalities, that it's less than or equal to and greater than or equal to. So these two quantities are equal to each other. So we have some minimum vertex cover C, and by LC we'll denote the vertices from the left part of our bipartite graph which belong to this minimum vertex cover C. And by RC we denote the vertices from the right part which belong to this minimum vertex cover C. And now we consider G1 subgraph on vertices of the left part which don't belong to C and the vertices of the right part which do belong to C. Let me show it. Here's a bipartite graph. This is left and right parts, and this is a minimum vertex cover of this graph. It has 3 orange vertices. Now LC is a set of vertices which belong to the left part and to the vertex cover. So this is just this one orange vertex on the left. And RC is a set of vertices which belong to both to the right part and to the minimum vertex cover. So this is these 2 orange vertices on the right. And now we consider the subgraph G1 on vertices on the left which don't belong to C and vertices on the right which do belong to C. This is this subgraph on 4 vertices. 2 white vertices on the left and 2 orange vertices on the right. Okay, G1 is this graph. And now we will show that for every subset of vertices of RC, the number of vertices, the number of neighbors of the set is greater than the size of the set. So for every C, which is subset of vertices of RC, the number of their neighbors is greater than the size of C. Let's prove it. So we see that here we can take 3 different non-empty subsets of RC. RC has 2 vertices. We consider subset S, which has both of these vertices, then we see, the number of their neighbors is 2 in the graph G1, which is greater than or equal to 2, the size of S. If we take S to be just one of these vertices, then it has 2 neighbors in G1, which is also greater than the size of the set 1. So we do see that this inequality holds for every subset of vertices on the right. The number of their neighbors is greater than the size of the subset. But why this? Assume that, for example, if we take 2 vertices from RC, they have only 1 neighbor in G1. But then we could take this one vertex in our vertex cover instead of 2 orange ones. We just take this one. It covers the same edges. And now we have a vertex cover of size 2. We have a smaller vertex cover. But we assumed that we originally had a minimum vertex cover. A vertex cover with a minimum number of vertices in it. So this can't happen. This way we prove that for every subset of vertices in RC, the number of neighbors there is greater. And now we can use Hall's theorem. Hall's theorem says that if this condition holds, then in this graph there is a matching of size at least the size of RC. We proved this theorem when we were studying bipartite graphs. Hall's theorem says this condition implies a large matching. So in this graph G1, we have a matching of size at least RC. And now we do the same thing on the other side. We define G2 to be a similar subgraph but with swapped sides. It's a subgraph on the vertices L sub c and vertices R minus R sub c. And again, by the same reasoning and by Hall's theorem, we can prove that there is a matching in this graph G2 of size at least LC. And now we can take these two matchings, they are disjoint, these two graphs are disjoint, so that these matchings are disjoint. We can take both of them and say we have a matching of size at least C. So we have a matching of size exactly C, so the maximum matching in our graph is of size at least C. So we just prove that this graph has a matching of size at least the number of vertices in the minimum vertex column.
We continue our graph theory part, and in this part we speak about networks which are graph with capacities. Let's see what it is. But to explain what we mean, we start with a simple example, and the example is just about oil pipes. So there is a network of oil pipes, and here in the A, the edges, these edges are pipes. The numbers, these numbers, are their capacities. So capacity is how much oil can be transferred along this pipe, in some unit time, like barrels per hour or whatever. So these are capacities, and we decide that oil is initially in A, there is a source of oil, and the destination, the place when the oil is needed, is B. And the goal is to move oil from A to B as fast as possible. So we want to find a maximal flow. It's more or less intuitively clear what we want, and also clear that this problem is really important. Of course, not only for oil, but for any commodity, I don't know, water, or just the people who want to flood some, if they want to go outside some area for, I don't know, for weekend, or just bytes in internet cables and so on. So there are many cases when this setting looks reasonable. Of course, they are more complicated, but we consider the simpler one with some clear physical meaning about oil. So what is the maximal flow? So for example, this 10. Can you put 10 units of oil per unit of time in this scheme? So there are 6 and 4. So if you are careless, you just send 6 here and 4 here, but then you find that the 6 come here, and there is no there is no way to send them anywhere. So this is not a good idea. So you cannot do like this. But you can do the next slide shows that 8 is possible. So you see a very simple solution. We forget about the 6, and we just send 4 in this path and 4 in this path, and in total you get 8. And here so there is a flow 4, 4, 4, 4, and 0 here. This edge is not used at all. And here are capacities. They are maximal things. So you see that actual flow should be bounded by, should not exceed the capacity. Okay. And you see that no oil is lost because all the 4 which come here go there, and everything is okay. And the flow, the total flow, is 8. 4 along this path and 4 along this path. So the question is, can we do something better? What do you think? Look at this picture. Can we do something better? And probably you see that we can. Look, there is some reserve. We use only 4 out of 6, so we can put a bit more oil here. But then we cannot put it here, but we can put it down. And then here is the reserve. So something can be really improved. And if you think about this, you see the flow 9. So flow for A to B is 9 because 5 goes here, then it's split into 4 and 1, and 4 comes from here, and these 4 and 1 are combined into 5. So the total flow is 9. And the question is maximum or not? What do you think? So we see that it's possible, and we know that, of course, it can be more than 10 because 6 plus 4 is 10. You cannot just send more from A. But can you improve 9, or 9 is the maximum? What do you think? And 9 is a maximum, and here is the explanation why. And this explanation is in terms of a cut. So imagine that A and B are in different states, and there is a boundary between the states, and there are 3 pipes which are export pipes, so to say, which cross the boundary. And they have capacity 4, 1, and 4. So definitely, if there are only 3 export pipe of these capacities, you cannot export oil faster. So nobody cares now what are the capacities here. If there are only 3 edges which cross the border and they are capacity 4, 1, and 4, then you cannot get anything more than the sum. So this dashed line here is a cut, and we compute the capacities of the pipes that cross this cut, and we see that the total capacity is 9, and so no flow, you cannot send more than 9 units. And we have an example for 9, and this argument shows that this example is really a maximum example. So now we are very well set with our case. We have a flow and we have a proof using a cut. We have a proof that this flow is optimal. Now our goal is to do the same in a general case. So we define the notion of network, which is graph plus capacities plus source and destination vertices. And we want to find a maximal flow. And to solve this problem, we should provide an example of maximal flow and the proof of maximality. And this proof of maximality, we know a tool for that. It will be using cuts. So this is what we want to do. And this is what was done by rather long ago by Ford and Fulkerson. And I will explain the theorem of these two guys with some simplified case. The simplification is that all numbers will be integer in our setting. The theorem is true for any capacity, they don't need to be integer. But the proof becomes more complicated. So we are considered a simple case. When the capacities are integers, then the maximal flow will be also integer. We will see this. First, we should define things more mathematically. We speak about oil and pipes and so on, but we want to be more formal. So let's fix the framework for that. So what is network and what are the capacities? So the network is a graph, and or just you can even forget about graphs. Just the vertices of the networks are just numbers 1, 2, and so n, and up to n. So we have n vertices. And one of them, of these vertices, is declared as a source, and the other, some other, is declared as a destination. It should be a different vertex. And for every 2 vertices, I and j, we have some number, capacity. So somehow this is how much oil can be sent from I to j. So it's just formally just a non-negative number, which we assume to be integer. And for simplicity, we do not consider the graph. We just say that if there is no pipe, then this in the array we have a 0 element. So it's no pipe and pipe of capacity 0 is the same thing. Okay, and what is important that we allow non-symmetric things. So if we have I and j, we allow the situation when we can send more. No, I is not here. We can send more from I to j, then no 10, and only 2 in other direction. And why such a strange thing? Because it's useful for intermediate steps. So we, as usual, we need to generalize the statement to prove it. Oh, you will see how it works. This is needed for the analysis. And the last also comment. So imagine in real life, you can have 2 pipes with the same source and destination. And in how do we, in our table, that doesn't make sense. We do not allow several pipes. But of course, we can just add some up the capacities of all the pipes and say just as one bigger pipe of a combined capacity. So it's not allowed, but it doesn't matter. It can be easily reduced to the case of one pipe. And the last thing also that in the table there is a diagonal element, pipe from I to I. It makes no sense. So we decide that these elements are 0. Okay, so this is what is a network. We fix the number n, we say what is the source, what is the destination, and we specify the array of capacities, just an array, and there are some restrictions of this array. So this is a network, and then we should explain what is the flow and what is the cut. So this is two next slides are prepared for that. What is the flow? Flow is just another array which says how much oil is sent actually, not what can be sent, but what is really sent now. And so it's also a number for every two vertices I and j. We say how much oil is now moving from I to j, and it should not exceed the capacity. Oops, sorry. It shouldn't exceed the capacity of the pipe. This is why the capacity are needed. And there is a rule which is taken from electricity rules. So if there is a flow from I to j, we say that this is of 1 unit. We say that this is the same as a flow of -1 unit from j to I, like in positive electricity and negative electricity, so to say. So we assume that this F are symmetric with changing the sign. And this is convenient for our purposes. You will see why it's convenient. And first we can know that this implies that if I is equal to j here, we see that this Fii should be 0. And now we should return to our condition that no oil is lost. So what does it mean? So if we take some vertex I, and let's look at all the pipes that go out of I, and each of them carries some amount of oil, but they should compensate each other, and using our sign rule, we can say that the total sum of all flows for all the edges should be 0. So for every I, the sum over j should be 0. Formally, here is also j could be equal to I, but this is 0 anyway. So this is a condition, and of course this condition should be everywhere except for source and destination, because there are external consumers and producers there. And for destinations, the number of oil, the amount of oil which is sent is just this sum, and for source, and for destination, the amount of oil which comes is here. So, and the law of conservation of matter says that if there is nothing is lost in the middle, then all the oil should come to be. So there is the same number. You can prove it formally, but it's more or less obvious. So this is what is flow. And the last ingredient is cut. So what is cut? It's our technique how to prove that the flow is bounded, how to prove that we cannot have a flow bigger than something. And we find a cut of bounded capacity. So what is the cut? Actually, we cut between A and B. So there are two parts, but we will consider for simplicity of the definition only one part, the part that contains A but not B. So there are internal vertices and external vertices in terms of the cut. And the total capacity of a cut is just we look at all outgoing edges which start if there is some C. We look at all the edges which go in this direction. So if they start at C and end outside C, and the sum of their capacities is just the total capacity of a cut. And the same conservation of matter means that whatever comes, the amount of oil which leaves A is the same amount which crosses C and the same amount which arrives into B. And so any total flow is bounded by the total capacity of any cut. And what Ford and Fulkerson proved, that this inequality, this never exceeds. Sometimes it's an equality. So sometimes the flow is equal to cut. So maximal flow is equal to minimum cut. So let me draw some pictures which should explain this. So what is the obvious part of Ford and Fulkerson? So this is the real line, and there are some possible flows. It's kind of symbolic, of course. picture, and there are some possible capacities of some cuts. And what we know that every flow is bounded by every cut. But what the theorem says is, Ford and Fulkerson, what they guarantee us, that there exists, actually these two things should match. So there is some flow and some cut which have the same, give the same number. And therefore we know that this is optimal, because we know that no flow can exceed this cut, and some flow achieves this. So this flow is maximal, and the cut is minimal for symmetric reasons. And this is the statement, Ford-Fulkerson theorem, that maximal flow equals minimal cut. This is, if you want to say it in 4 words, it's what you should say. Now we have the statement of the theorem, so what else can we do? We should provide a proof. So here is the proof. And to provide a proof, we start with, we understand our theorem in some special case. It's generally a good idea. If you are given a theorem, before proving it, you should look what the theorem really says. And to understand this better, you should consider this case, that case, and so on. But it's not only an example, but also a tool for the general case. So it's also happens often that after you prove some special case, you can reduce the general case to the special one somehow. Anyway, what is the special case? It's a case when there is no flow. There is not possible to send any oil from source to destination. So no positive flow. And the theorem, so maximal flow is 0 then, and the theorem says that the minimal cut should be 0. So there should be cut when there is no outgoing edges of positive capacity. So if there is no flow, there should be a cut which makes this flow impossible. Can you say why it happens? It's actually not difficult. If you think, you will guess this. Oh, here is the statement again. And now we need to explain this. To explain this, we introduce the notion of reachable node. So by definition, it's the source node A is reachable, and every node which can be reached from a reachable node by an edge of positive capacity is reachable. So we just somehow look where the oil can arrive, just independent of quantity, just when there is a chance to send some oil. And technically you can say that we have considered a directed graph made of edges of positive capacity, and you look what vertices are reachable from A in this graph. And by assumption, our B is not reachable. There is no path from A to B which goes through edges of positive capacity. And why then there is a cut? So if B is reachable, let me say it in contraposition. If B is reachable, then there is no zero flow. Let's look at this path from A to B with edges of positive capacity. Technically, it can happen that this path is not simple path. It goes twice through some vertex or even through some edge. But of course, you can delete all the cycles, and so you get a path when you never come to the same vertex. And then you can send, if the capacities are positive and integer, you can send at least 1 unit of oil along this path. So if the vertex B is reachable, then there exists a non-zero flow, and in integer cases, it's 1 unit flow is possible at least. But what if B is unreachable? The other case. Then there is a zero cut, and it's easy. What is this cut? Do you see it? Of course, it's just made of all reachable vertices. By definition, there is no edge going of positive capacity going from reachable vertex to a non-reachable. So just by construction, we know that this cut has capacity 0, and A is inside and B is outside. So this is just the cut we looked for. So our special case is now completely proven. So the cut, let me repeat, the cut is the set of reachable node from A, and reachable means reachable in the graph of positive capacities. So the special case is considered. Now we want to go to the general case. And the proof idea is very simple. So in one sentence, we increase the flow until we find a bump into an obstacle, and this obstacle is minimal cut. But we should, of course, explain what we do. So our special case is a good start. Either we bump into this zero cut immediately, or we can increase the flow, and as we have discussed, there is one flow of size 1. So it's a good start, but maybe it's not optimal, of course, and we should increase it further. So this is our special case, what special case says, and then we repeat this procedure somehow, and each time we increase the flow by 1 until we bump into some matching cut. Of course, as we don't know why we will bump into some matching cut, and we need to explain what happens. And this explanation is just the reduction to our special case, and the tool of this reduction is what is called residual network, a network of reserves, so to say. And let me explain. I prepared some picture for that. What is the reserve? So imagine we have an edge somewhere in the graph. It's just a small edge in a big graph. And imagine that it's capacity, and this is flow. So you see that this edge is not fully used. We can still send some oil here, and maximal oil we can send is 2. We can send more flow. But also, so to say, we can decrease the flow by 10 here. Why 10? Because we have now plus 4, and we can have 6. We can stop this 4 and use the 6 in other direction. No, we assume that this edge is symmetric. It's plus minus 6. It's not clear from this picture. So the edge is symmetric. It's 6 in any direction. Now we can use it in 4 in one direction, and then we can switch direction and make 6. So the difference between plus 4 and minus 6 is 10. So this is this residual network. It has capacity 2 in this direction and capacity 10 in the other direction. Actually, it's not so unreal. So there are long stories when there is some, I don't know, there is some gas sent in from A to B, and then somebody wants to send the gas from B to A, the other company. And the simplest thing is to just to decrease the flow, so and use the gas whereas before not sending it. But there are a lot of legal difficulties with that. But in our mathematical model, there are no legal problems, and so we have a residual edges of 2 and 10. And for the general case, I prepared the slide. This is exactly the situation we had. We have this flow 8, and so here was 4 goes here and 4 goes here, and capacities are 6, 4, 4, 6, 1. And we just compute the residual network. We can send 2 more, or we can send 10 here, or in this here we cannot send anything, but in the back direction we can send even 8, and also here things are symmetric. And here it's not used, so we can send 1 in any direction we want. And now in this, what is the meaning of this residual network? And there are 3 things, two things, sorry. So the first is that what is a flow in the residual network? A flow is just increase compared to the current flow. So we have an original network, and there is some current flow, and we look how much this current flow can increase or decrease. What are the changes in the current flow? And these changes are, the bounds for these changes are shown in the residual network. So if there is a path in the residual network from A to B, this means that we can increase the flow in our original network by the capacity of this path. And this is about flows. And another thing is about cuts. So if we have some zero cut, here we don't have a zero cut, but in our second example we would. If we have a zero cut in the residual network, it means that all the edges that go across this cut in the right direction are fully used. because they have zero capacities in the residual network, which means that they are fully used in the original network. So this is the full cut. And so now we see that we consider the residual network. There are two cases. Either there is a zero cut, and then we have a cut, we bumped into some cut in the original problem, or there is a path in the residual network and we can increase our flow along this path by 1, so we increase our flow by 1, and that's what we wanted. So let me repeat the story, the pieces together. So it's a kind of algorithm. So we start with a zero flow, and then we repeat the following iterative procedure. First, given a current flow, we compute the residual network. First time it will be the original network. And then we apply our result about special case. And either we find a path which can improve the flow, which is called the augmenting path, or we find a zero residual cut. And in this case, the cut means that in the original network, we bumped into our flow bumped into a minimal cut, and maximal flow are the same. And then we stop, and after that, we have maximal flow and minimal cut that match each other. So this is the algorithm. You should think about this. It's so simple that there is not clear where is the trick. But really, there is nothing counterintuitive. It's just we do whatever we should do, and we are done. It's very easy theorem if you know how to prove it. Only thing which we should say, it's also almost obvious for integer capacities, the termination. So if capacities are integer, then each time we increase the flow at least by 1. We know that in this residual network we have a path, and we can assume that it doesn't come back to the same vertex, so we can just send at least one unit of oil along this path. So we increase the flow at least by 1, and so we cannot do it infinitely long. We will finally stop. And also, this algorithm shows that in integer for integer capacities network, maximal flow is also integer, which is important for some application. Now we will explain some application of this False-Farquharson theorem, but here the word application is understood in mathematical sense, so it's not real application. We just use one theorem to prove another theorem. And this theorem is about perfect matching. And again, a warning, you should not mix mathematics and real life. So we are using this marriage terminology without any claims about the institute of marriage in the society. So in our simplistic world, we have n men and n women, and there are some pairs for which both participants agree to marry. And for one man can agree to marry with several women, that's okay, but we want to find a perfect matching when this doesn't happen. A perfect matching is one-to-one correspondence. It's a set of of n pairs which include all n men and all n women once. And this is just a bipartite graph. If we draw it, so we have a bipartite graph, and we want to delete some edges, so we get some one-to-one correspondence between the parts. And here is the picture. This, I'm sorry to using so bad names for men and women. So we have men A, B, C, D, E, and women P, Q, R, S, T. And I just drew, here are some example what pairs are okay for both participants. So is there a perfect matching or not? What do you think? Look at this picture. Is there a perfect matching? It's easy to find 3 pairs. For example, these red lines show 3 pairs. But can you find 5 pairs or even 4 pairs, not without collisions? Actually, it's not possible. 3 is a maximal number, and there is some simple argument. And look, there's green dots here. So let's look at men A, C, D, and E. And if you look carefully, you see that there are 2 women, Q and T, and all these men do not agree to any other. So there are 4 men and only 2 women. So 2 of these 4 men will remain unused. So the maximal matching is without collisions has only 3 persons out of 5. So no perfect matching. And this whole theorem says that this is the only obstacle to perfect matching, so to say. So let's give a mathematical statement. Imagine we have a bipartite graph with n vertices on the left and n vertices on the right. And when it doesn't have a perfect matching, this graph doesn't have a perfect matching, if and only if there is an obstacle. And the obstacle is there exists some k, at some k vertices, okay, sorry, k vertices on the left, and there is not, they don't have enough right neighbors. So if we look at this k vertices on the left, and we look at all the neighbors of any of them, and there are less than k neighbors, then of course you cannot find pairs for all these k people. So it just was the same obstacle we had with 4 and 2. So if such an obstacle exists, there is no perfect matching. And it's obvious it's an obstacle. But what is not obvious, that this is the only possible kind of obstacle. So if there is no obstacle of this type, then the perfect matching exists. This is what the whole theorem says. So this is a statement, and then we need to prove it. And the proof is the reduction to Ford and Fulkerson. And let's see this. Look at this reduction. So what do we have the same graph in the middle, and now these edges are edges of high capacity in one direction. Okay, it's difficult to draw arrows in a reasonable way, so just all these edges go from left to right and have high capacity. And what really restricts the capacity, the flow, is here. All the source is connected to all the left vertices, but with edges of capacity 1. So this edge, if we have integer flows, it's only 0 or 1. And the same for B. There are n, so there are n vertices here. So there are n edges which go from B to the destination. Each has capacity 1, so it can carry 1 or 0. And we look for flows in this network. And they are very closely related to matchings. So this is what pipes are for left to right and large capacity in the middle. And if we have a matching, here is the claim. So the matching is actually a flow of size n, integer flow of size n. Why? So if we have a matching, then of course we can easily organize a flow. Everything goes, all pipes are used. Then in every vertex we have some matching pair. So we just send to the pair, and then everything is collected and sent to B. Very easy, if there is a matching. And another thing, it's what is easy to understand, that matching of flow of size n means a matching really. So if we have a flow of size n, this means that all the edges are full. And if the flow is integer, matching is an integer flow of size n. If the flow is integer, then of course this should go somewhere in one direction. You cannot split it into different parts. So you should go in one direction, and of course you should not come to the same vertex, because if two ones come here, then they will stuck here and the oil will be lost here. So we have only pipe of capacity 1 here. So matching is an integer flow of size n, exactly. And so we apply Ford and Fulkerson and conclude that if there is no matching, there is no flow of size n. And if there is no flow of size n, then is a cut of size less than n. And we will see that the cut is an obstacle of the type we are looking for. So what is the cut in general? So cut is a set of vertices which contain A and doesn't contain B. And it may contain some vertices in the left part and in the right part. For our Ford and Fulkerson, there is nothing special in bipartite graphs, just some graph. So I use the same letter C, but of course there's C's for the source, and there are left C and right C vertices. Now we can think what is in the cut. So cut is just made of 3 parts, and there are what are the outgoing edges? So I tried to show them. So they can go out from here, and there are all edges which go outside the left C. This is cut edges. And if there is some vertex which goes from left C to a vertex outside the right C, then it's also a cut vertex. And the last chance to go outside C is to start here in C and then go to B. So there are outgoing edges of 3 types. But if we look at the minimal cut, then the second type is impossible, because these edges have large capacities. So if one of them is included in the cut, then the capacity of the cut is very large, so it cannot be minimal. So in the minimal cut, there is no edges of this type. And what does it mean? No edges of this type. So no edge going from left C to something outside the right C. This means that this right C contains all the neighbors of left C, all the neighbors of vertices here are inside this right C. And this is just, it should remind you of the obstacle thing. So imagine, no, let's try to make some computation. Imagine we have K, K here, and then we have n minus K edges which are in the cut. And there is no edges here. And the cut is smaller than n, and each edge is capacity 1. So if cut is smaller than n, then these edges are smaller than k, because n minus k is here. So to get some less than n, we should have something here smaller than k. And look, so we have here k vertices. We have here less than k vertices, and we know that these edges do not exist, that all edges going outside, going from this C, go in this C. So it's exactly an obstacle which we wanted to find in Hall theorem. So Hall theorem is a corollary of Ford-Fulkerson. Oh, this is just summarizing. If we have a cut less than n, then this left C is bigger than right C, and this is the other requirement for the obstacle in Hall theorem. Now let's make some more general comments about these things. So I started with the importance of the initial task. It's really a practical problem, and so people are really care about this, and there are better algorithms. Our Ford-Fulkerson algorithm, first, it's only for integer capacities, and it's not optimal, and it was improved many times, and it's a significant part of the algorithms, efficient algorithm theory. And having a good algorithms for cut and maximal cut, maximal flow and minimal cut, sorry. We also have good algorithm for matchings. And also, this is not the most difficult thing. So for example, we can consider the problem for matching in when there is not a bipartite graph. We have just a graph, and we want to find an edges, maximal number of edges, preferably including all the vertices, but just the maximal number of edges which do not have common vertices. They are called matchings in a graph without parts. And it's what should be called, can be called matching for same-sex marriage. Again, it's just a terminology, no claims about real life. And this also we can consider the cases when there are several types of commodities. For example, we have a railway, a set of railway lines, and each railway line can, of course, it's not like a pipe. You cannot send water and oil in the same pipe. But in the railway line, you can make a combined train. So there is just a limited capacity for all commodities sent. And then you can have several commodities and you want to send them somewhere. Or you have not one source of oil and one destination, but you can have several oil sources and several destinations, and you need to organize things, and or you want to try to minimize the cost of this or whatever. So there is a lot of practical problems, and they are much more complicated. We consider only the simplest case. But most of these problems are special case of what is called linear programming. It's a very important thing we will not cover in our course, but you can probably find many sources and Coursera courses about linear programming. And what I want to say that this effect, that maximal solution match the bumps into minimal obstacle, is a general phenomenon for linear programming problems. It's called duality. It's very important to understand it if you do linear programming. And finally, you know, like in a good opera, if there was some theme in the overture, then the theme usually appears somewhere in the opera. So we started with tilings. Let's explain why Ford-Fulkerson, no, actually whole theorem is important for tilings. So what if you forgot this already? This is what we consider the domino problem, which we have a region in a cell paper, and we want to tile some region, this region with dominoes. And the question is whether it's possible, and how to find, looking in the region, how to find the tiling or prove that it's impossible. And the tool is a reduction to a matching problem in a bipartite graph, actually. And this graph, let me tell you, it looks strange, but let me tell you, what are the vertices of this graph? Left vertices are white cells, and right vertices are black cells. And edges between black cells and white cell and black cell exist when they are neighbors. And if you draw this graph, matching in this graph, perfect matching, any matching in this graph is a tiling, and perfect matching is the full tiling, so to say. So any set of edges with disjoint endpoints corresponds to some tiling of some part of the region, and a full tiling, perfect matching corresponds to full tiling. So do you see why it happens? Just you can think about this yourself, but I prepared a picture showing this, but maybe you already understand this what I'm saying. Anyway, here is the picture. So here are the regions. So this is what you want to tile. This don't exist for us. And of course, in the picture you can tile it easily. You can put things here and things here. So the problem is easy, but I just need small example. But just in general, what do you see here? So imagine we have a tile. The tile is a domino 1 times 2. And we can look at this tile as a kind of connection between two cells. One of them is white and other is black. So the possible connection, the possible tiles, or the possible connection between cells are just neighbor pairs of white and black cells, and we can draw all of them. So here, it's just looking at the region, we create this picture where the tile could be. And now the only thing we need is to find a matching, because if you find the matching, if we delete some edges and get a set of pairs, and this is just what we need, because each pair makes a tile, and we are done. And what is nice, then for this case, we don't need complicated same-sex marriages. We have a matching problem for bipartite graph, and we know how to do this with Ford and Fulkerson. So now you know how to solve any problem about tiling. You just construct a graph, you convert it to a network, and then you apply Ford-Fulkerson to this network, and either you get a flow and a matching and a tiling, or you get a cut, or a set of obstacle in the matching problems, which now means that you find some set of k white vertices for which there is not enough black neighbors. So if you find in a picture you find k black vertices, and they are organized in a way that they don't have enough neighbors, black neighbors, then it's obvious that there is no tiling. This vertices cannot be covered at the same time. So this is a reduction. It's a standard technique for algorithm. You reduce some problem to some other problem, and so an algorithm which gives a solution for the second problem can be now brought back for the first problem. So for a region, you know how to find either a tiling or a proof that tiling doesn't exist, and this is what we started with. So now somehow you can be satisfied that the initial question which we posed before the course is now solved. Of course, we choose the question this way, but still, you should feel some. You should be satisfied with this. Here is the final take-home message. You apply for this reduction. You applied for Fulkerson. It finds the tiling if it exists, and it finds an obstacle if there is no tiling. But does it not directly. It does it through a chain of reduction. So the idea of reduction is very important, and you will see these reductions in computer science. When you prove that some problem is difficult, you show that some other problem can be reduced to it, and if you want to show that the problem is easy, you reduce this problem to some other problem. So we used in the second thing. We started for Fulkerson, we solved it. With this flow problem, we solve it, and then we reduce the matching problem to Ford Fulkerson, and then we reduce tiling to matching. So finally, we solve the tiling problem. Okay. Now this is the last topic in the graphs course. So we will consider some practically important and theoretically interesting problem, which is called stable matchings. Let me start with some real-life example, and then I'll explain the mathematical part of it. So I took an example which I know personally. It's about university entrance in Russia. So up to some time there was an old system, and the old system was that each university organized its own entrance exams, and all of the exams and around the country was at the same time. Well, there were some small exceptions, but let's forget for now. And then you can participate only in one exam. So and you can send only one application and go to this university and take the exams. And if you are accepted, you are fine. But if you fail, then it's too late for other universities. So you have no university this year. And if you are male, you risk to being taken to the army. So it was a big deal, actually. And at some point, they probably with best intentions, they changed the system. And this new system was different. There were some country-wide tests. You can participate in these tests and get some grades. And then you can apply to different universities, and each university gets your grades and may decide whom to accept. But university, then the university makes offer, and then you decide which offer you want to take if you have several. And maybe you can guess what was the disaster this year. It was a huge disaster, actually, because if applicants choose some university, then the other universities do not get them. So from the university viewpoint, you can make several offers, but if you make more offers than you have places, then you risk that you cannot accept all people. And if you have this number of offers, then of course most offers are not taken. So you end with very few students. So you need a new wave of offers, and then and it's a short time actually in summer. So it was a complete mess at that moment, and it's still there is no well thought system how to deal with this. Now there are some restrictions and things are a bit better, but still it's a big problem. Anyway, what I want to say here is just that it's a very important problem of matching somehow supply and demand in this kind of situations. And we will consider a simplified model. This simplified model is when university have many positions, and we consider a job where it's, each employer has only one position. So we have n candidates, and we have exactly the same number of positions. And let's be in a simple situation. Each candidate has knows everything about all the positions and has a complete list of preferences, which position is the best, which is the second one, and so on. And at the same time, so the positions also, the employers also have the full information. They need whom they want, if possible. If not, who is the next candidate, and so on. And the goal is to find the matching. So the matching in terms of graphs, it's a perfect matching. So we have n pairs, a candidate, a position, and of course, each candidate should go to only one position, and this position should be filled by one candidate. So we are looking for a matching, and there is a condition. In graph theory, it's perfect matching, and there is a condition which is called that the matching should be stable. And let me explain. This is the main thing. We should understand it very well, because we will develop algorithm which guarantee this property. So what is stable matching? So let me show what is unstable matching. So imagine we have some, I don't know, let us be candidates A and B and jobs P and Q. And so there are some preferences. So imagine that this A prefers the job Q, so the current job is P and the current job is Q for B. But actually A prefers Q. He likes Q better, or she likes Q better than P. And also Q, the employer Q, would also prefer A to B. So there is some kind of reason there is instability here, because this pair AQ is better than the current situation, both for A and for Q. So if it's better for one of them, it's not enough, because the other will not agree to this change. But now it's better for both. So they have all the reasons to switch to this new pairing. And then, of course, if we agree that everybody wants to get a job and every position should be filled, then B and P are forced to make a new pair. So now it's a natural question. So imagine we have a complete list of preferences, and the question is there a stable matching or not? And of course, if it is, how to find it? This is the question, most natural question about this setting. Now let's speak a bit about the connection between mathematics and real life. So we started with a real life example, and it indeed is practically important. So important that it deserved a Nobel Prize. So there is a Nobel Prizes, and also there are Nobel Memorial Prize in economics. And this prize for 2012 was given to two people, Roth and Shapley. And here is a quote from the press release of the committee. And from this quote, you see that Shapley was a theoretician, and Roth applied the theory developed by Shapley and actually by Gale to the practical situation. So you see that there are several practical cases are mentioned here. Doctors with hospitals, students with school, and even a very important but sad case about organ donors and patients, where each matching is about somebody's life. So what was the origin of all this field? It very funny. The first paper was written by Gale and Shapley, and it was written in 1962, rather long ago, and it was written not in some research journal with high impact, with refereed and so on. It's just a popular journal for a wide audience, as they say in the description of the journal, American Mathematical Monthly. And you can read this paper. Here is the reference, and it's just, you see, it's just very elementary paper, and still it turns out to be extremely important and deserved a Nobel Memorial Prize. Now, a very important warning. So it's about terminology. So you see in the name of the paper, they say the stability of marriage. So they use the marriage terminology, and we will also, following the tradition, use this terminology. And the terminology is, instead of applicant and job, which are we discussed, we will speak about men and women who want to marry. And we will consider the simplest setting when there are men and women, and they want to form pairs each man would marry one woman and so on. And this is all in this terminology, what is called matching in draft theory is called marriage or set of marriages. And what is very important, so we make no claim in this terminology, unlike the case with applicants and jobs. This is completely nothing to do with practice. We make no claims about real life, and so this is not if we say that some algorithm designs a set of marriages which is stable, we don't mean that you should use this algorithm in practice for anything. You know, mathematicians usually consider everything in the real world just as a good illustration to some mathematical theories, and they don't bother whether this heuristation is really adequate or not. Just if it's a funny terminology, that's okay for mathematicians. And now we will also follow this tradition. So please don't take this claims personally. So just the reason is that, so say, her husband is much shorter than the applicant that filled this position, and the algorithms are complicated, not really complicated, but just you need to keep track of the details, and short terminology is very important. So we will use this short terminology without any practical consequences. Also, this terminology is more symmetric. You see that men and women are symmetric, so every algorithm can be, of course, reversed, and it's clear how to reverse it, just to change the names. Now let us start with some basic examples of what is good and what is bad, and using this marriage terminology. So first, let's consider some cases when there is a unique stable marriage. So the simplest possible case, let's repeat the setting. So we have n men and n women, and each participant has an ordered list of preferences, and we are looking for perfect matching or marriages where everybody is married. And the requirement we want to achieve is stability, and stability that there is no pair such that both people in the pair prefer each other to their current partners. So this would make an incentive to change the marriage. But so stability means that no such pair exists. And of course, the simplest case when there is no problem is where just n is equal to 1, and there is no choice, no problems, and so on. And another case, more interesting case, is where all the men have the same preferences. So the list for all men is the same. Of course, you can also speak when the list for all women is the same. So in this case, I claim there is unique stable marriage, and for a very simple reason. Let's try to see why. So this is the case of the same ordering. Here is this ordering. So all men have the same ordering. All of them prefer woman 1, and if not, then woman 2, and so on until the woman n. And let's look at the woman 1 preferences. So she prefers somebody. We don't know whom, some mi. And like all other people, mi prefers also w1. So this is a kind of good situation. One, there is a man and a woman which think they are the best mutually. So in any stable marriage, they should be married, because if they have different partners, then they will form an unstable pair, because they prefer each other to any other partner. So in any stable marriage, we will have this connection, this pair between mi and w1. And also what is good, that they cannot create instability. So if we find a stable marriage for the rest, for the remaining n-1 men and women, then and we add this pair, there is no new instability, because both of them are completely happy. They do not want to change the pair, so they will not. They cannot create unstable pair with anybody. So it remains to find the stable marriage for the rest, And it can be done, of course, in the same way. In the same way, we look what are the preference of women too, and take the best, her first choice, except for already used MI and so on. So this is a kind of induction, or in programmer term, it's recursion. It's an easy recursive algorithm to find the best matching for this special case. Symmetric case also exists if all, as I have said, if all women have the same preferences for men, then of course the symmetric thing happens. We should look who is the best for the first man, and then make a pair, and then apply the algorithm recursively to the rest. And let's now go to a bit more interesting case when n is equal to 2. So we know that if the preferences are the same for everybody, for all the men and all the women, this is already, we know what happens. So let's consider a different case. So now men A and B have different preference. A prefers P to Q and B prefers Q to P. And the first case with everyone is happy when the women have different preferences which match the preference of men. So A prefers P and P prefers A. And then, of course, what is happening, that is the best thing can happen, just have they follow their preferences, and this is the only stable marriage. So in this case, we have unique stable marriage. Here it is, in good quality. But another case is possible, and in fact, in this case, there are two stable matchings, but both are bad. So imagine that the men have different preferences, as women have different preferences, but now they don't match. So A prefers P. A would like to marry P, but P prefers B, and B prefers Q, and Q prefers A. So there is kind of inconsistency between the desires on both sides. And in this case, there are actually two possibilities. So we can have this matching, and in these matchings, you see, men are happy, but women are not happy. But this matching is stable because no man wants to change. So this is a stable matching, but it's not good matching. And also we can take another one, which is like this, and this here everything is symmetric. So now women are happy and men are not happy, but there is no instability because no woman would like to change her partner. So we have two stable but bad matchings, unfortunately. And it's of course it's a well-known situation, and you can even hear a nice song of Lied of Heine and Schumann. Ein Jüngling liebt ein Mädchen, it's called. So in the literature you can find a lot of examples of this type and even worse things. Again, we return to our main goal is to find a stable matching. There is a very simple approach which is sometimes called with the French name laissez-faire. So the idea is that let's start with any matching, and if there is something non-stable, let things happen. So if there is unstable pair, a pair of people who want to marry, who prefer to be paired to their current partners, let them do it. And of course, the people who are left should also form a pair if we want to have a perfect matching. So let's do it. But of course, after that, another pair, unstable pair, can appear, or in the beginning there could be a lot of unstable pairs. So we just try to let things happen. So this is the former partners. And when we should stop when there is no unstable pair. So we repeat this procedure until some stable matching is obtained. And the question is, of course, whether this happens. So is it possible that everything will happen? these changes will happen and happen and happen, and we can never get a stable matching. So this is the question of stabilization, and the answer is negative. It's not guaranteed. And let's consider an example. It's taken, probably there are many, but this specific example is taken from Donald Knuth book about stable marriages. It's a nice book in French, and there is also an English translation, even a Russian translation. So the example is there are 3 men, A, B, and C, and we have 3 women, P, Q, and R. And here are the preferences which are known, which are important. And for B and for R, any preferences will work, because they will not really play any role in this sequence of marriages and a sequence of changes. And we will see that there is a loop. So we start with some position, and after some changes, everything returns to the original state, and so it can happen the same, and we can get an infinite sequence. And it's rather you should just check that everything is okay. Let's try to follow. I prepared the slides, but let's look how it works. So this is the initial setting. A is paired with P, B with Q, and C with R. And you can look here and find an unstable pair, and it should be shown in red on the next slide. Yeah. So why it's unstable pair? Because you see that Q is better than P here. And also for Q, A is better than B. So there are all the reasons to pair A and Q. For both sides, it's an improvement. And then B will be paired with P. So this should be shown in the next slide. Yeah? Yeah, here is the next slide, and this is shown. Now we can look for another unstable pair, and it should be shown in red. Yeah. So why it's unstable? So for Q, C, this new candidate, is better than A. Here is it. And for C, Q should be better than R. Here is it. So you see that for both C and Q, red line is an improvement. So they form this pair, and then R and A are left alone, and they form another line. So, and this should be on the next slide. Let's see. Yeah, everything is okay. New unstable pair. You can stop the video now and try to find the new unstable pair, but here it is. C prefers P to Q. Yeah, indeed, C prefers P to Q. And P should prefer C to B. And indeed, P prefers C to B. Again, unstable pair. Again, it appears. And the people who are left, B and Q, form another pair. Here is it. And now we are very close to the end of our loop. So there is a pair AP. Look, A prefers P to R, and P prefers A to C. So again, C to R form, the people who are left form a new pair, and we get this. And it's exactly the thing we started with. So things can repeat and repeat. It's kind of strange thing because, you know, somehow at each stage, let me say an argument why it should stabilize, but it's a wrong, of course, argument. Stabilize because the situation improves. Improves since in each change, people become more happy. These two people who make a new pair become happier. But of course, this argument doesn't work, and probably you guess why it doesn't work. So I will not tell you this now. Think a bit what is wrong with this argument. So we need to look for another algorithm to find the matching, and it's called Gale-Shapley algorithm, as according to the names of the people in the first paper, and we will consider it. Gale-Shapley algorithm is our next goal. So we will explain what the algorithm is and prove its correctness. and then we will explain why it's in a sense bad. It's very bad actually. So let's first explain the algorithm before going to all other things. So the algorithm is like this. At each stage we have a partial matching. So we start with an empty matching, there is no pairs, and then some pairs appears, and sometimes pairs are changed, so people in a pair can form a new pair. So how it happens? Actually, it's somehow each step is initiated by some man without a partner, and this man makes a proposal to some woman which may have a partner or which may have no partner. So a proposal is made on each step, and this proposal is accepted or rejected. So if the order is the proposal is accepted, then the new pair is created, and maybe if the woman has some partner before, this partner is abandoned and the old pair is destroyed and new pair is created. So at each step we either get a new pair or change the existing pair to a new pair. Of course, we should explain how there are two things to explain. Yeah, here the acceptance may destroy an existing pair. That's what I already said. The hope is that at some point everybody is married and we get a stable matching as we wanted. But the question is how the participants make their decision. So whom, if we find a man without a partner on a given step makes a proposal, to whom? And the second stage, if some proposal is made, how the woman should decide whether to accept or reject this proposal. This is two questions which are not covered in the general scheme. We will treat them now. Let me say one more thing, that algorithm is non-deterministic in a sense. So we do not specify in which order men make their proposals. So there can be several men without a partner. So we take one of them and he does whatever he should do according to the rules. But there is a choice at this stage. So any choice is okay for the algorithm. It's kind of non-deterministic algorithm. We will discuss later. Somehow it doesn't influence the result, but we will wait a bit. So first, the rules for men. They have the ordering. Each of them has some ordering, who is the best candidate, the next candidate, so on. And what they do, each of them just makes proposals according to the ordering, just ignoring the existing pairs, just ignoring everything. Just he tries first the best candidate, then the next candidate, and so on. And if the proposal is accepted, then man is happy for a while. He never leaves the current partner by his own will. But the current partner may leave him, and then he makes a new proposal. He becomes rejected by current partner, and then he never repeats a rejected proposal. So the proposal can be rejected in two ways. It can be rejected immediately when it is made, or later the woman first accepts and then choose somebody else. So this is also a rejection, but another type of rejection. And anyway, men never repeat to the proposals which were rejected. If they want to implement this algorithm, actually we know this, not men, but some abstract entities in our program. So they should remember in their memory two things: the position in the list, so who already had already rejected them, and also, of course, they should remember who is the current partner, if it exists, or if the current partner doesn't exist. Also, they should remember this fact. This is behavior of this men, program entities. Now, next thing is how the woman should behave. And they have a different set of rules. They accept a proposal in two cases. First, if there is no partner. If they have no current partner, they agree to everything. they always accept. Or they accept if this proposal creates an improvement compared to the current partner. So if somebody who is more preferable than the current partner makes a proposal, they forget the old partner and change the pair. So this is another action they take. And if none of them happens, which means none of these cases happens, it means that the current partner is better in their list than the new candidate, then of course they reject the proposal. Very, very natural and easy algorithm. And to implement this in a program, the only thing a process should remember is just the current partner. So they compare this current partner with a new candidate and decide who is better and who is worse. And note that for women, things are getting better with time. So for men, they try candidates which are worse. They start from the best candidate and go down. So if some candidate accepted him, then this candidate is better than all the subsequent candidates, because this is just the ordering of proposals. And for women, the situation is different, opposite somehow. So the women get in some pair, and then this pair can only improve. This pair will be broken only if a better candidate is immediately available. So things are getting better with time for women. We have described the algorithm, but we don't know now whether it's correct or not. We should prove that it's correct, and there are three parts of this proof. So we need to prove three things. First, we need to prove that algorithm terminates. Who knows, maybe it will happen indefinitely, it will continue indefinitely, and then we don't have final matching. Second thing is that in the end of the algorithm, we do have a perfect matching, that everybody is paired. And the third thing is stability, that what we get as a perfect matching in the end is really a stable matching. So we need to prove three things, and we will do it one by one. So let's start with termination. It's almost obvious, but let me say it slowly. So let's look at every man. So when he acts, he makes a new proposal. And so he moves in one direction in the list, and there is no way to go back. So he can make at most n proposals, because the proposals are never repeated. And we have n men, so they can make in total only n square proposals. So there is no way to continue longer. And this is rather fast, especially if we compare this with the total number of all possible matching. So if we have n object on the left and n object on the right, you know from combinatorics course that there are n factorial possible one-to-one correspondence between them. And this is much bigger, of course. So n squared is quite practical, but n factorial is infinity for practical reasons. So termination is easy. Now, why at the end we have a perfect matching? It's a bit more complicated. Let's look at it. So imagine it's not the case. So imagine some man remains without a partner after this algorithm. This means that he made proposals to everybody in his list, and each of these proposals was rejected, either immediately rejected or rejected after some time. So all women rejected him either earlier or later. So what does it mean? What does it imply? So we can conclude that all women were married at some point, because if they rejected him, either they were married at the same time immediately, or they were married with him. So anyway, they were married at some point. And we know that for them the situation can only improve. So if they were married, they remain married later. So they remain married until the end. And then of course we get a contradiction, because all women are married and some men is not. And we have the same number of women and men by assumption. So this is how it's called, pigeonhole principle, says that it's not possible. So we have a perfect matching. And last thing is stability. It's also not very difficult, but let's look at it. So assume that it's not stable. The final matching is not stable. This means that there is some dangerous pair at the end of the algorithm. Let's denote this pair MW. So what does it mean? That for M, W is better than his current partner. And for W also, but now we look at M. W is better than the current partner. So this better W was in the list before, because before M proposed to his current partner, he also should have been proposed to W, because it's early in the list. And then W rejected him either immediately or after some time. So W rejected M at some stage, which means that at some time her partner was better, either when she rejected immediately or when she found a better partner than M. So at some time W has a partner that is better than M. And then, since the things improve with time, all the later partners are also better than M. So the pair is not actually dangerous, because the final partner for W is also better than M, so there is no reason for W to change. We get a contradiction with the assumption that the pair is dangerous. So this is the proof of stability. Now we have done, and we can formulate this theorem. A stable matching always exists, and the proof is to use the algorithm to find it. And let's make some remarks about the theorem. So first, as we have seen, the stable matching is not unique. So our algorithm finds one of the stable matching, not the only one. And now it's not clear whether this matching which is found depends on the non-deterministic ordering of the actions. Actually not. And we will see why later. It's more difficult part, but we will see this. And let me stress that this algorithm is extremely unfair. It favors men in a very strong sense. But of course we can consider a symmetric algorithm when women make proposals and men decide whether to accept or reject them. And of course this algorithm will have completely symmetric properties, so it will be unfair, also very unfair, but now in the other direction. Now I'll try to explain why this algorithm is unfair. It's actually double unfair. It treats the men the best possible way and the women the worst possible way. So let me explain what does it mean. Consider some men, and we know that there could be many stable matchings. So in this stable matching, the same man is connected to different women. And so there is some range of possibilities. And actually what is the claim that the algorithm gives the best one. So for what the algorithm gives is the best one a man can hope in any stable matching. And there's some corollaries. First, the non-determinism in the algorithm is not important, because this best stable matching is best pair for stable matchings is something which is defined independently of any algorithm. So if our algorithm finds this, then this is it is the case for all possible ways of executing the algorithm. And also you can look at it in a different way. So we have some invariantly defined thing. For every man we take the best possible partner. And the claim is that it's indeed a perfect matching, which is not obvious. Maybe abstractly we can imagine that for two different men the best possible partner is the same. But still it's not the case. So this is another corollary. And let me reformulate the claim, and in the different way which is more convenient for proving. So remember that during the algorithm our man M made proposals to different women in his list, and he was rejected by some of them, and then he was finally accepted till the end of the algorithm by some woman W. And no, W is accepted by some woman. What I want to say that if it was rejected by some woman W, then this woman is better than what he finally got in this algorithm, and this woman cannot appear in a stable matching. So stable matching cannot give any answer which is better than what the algorithm gives. So it's just the same claim as it was stated. So this claim is just repeated in a different way. But this way is more convenient to prove. Let's try. So again, this claim. And what is important to understand for the proof, that there are two pictures in this proof. There is a static picture, which is some stable matching. This stable matching, which we consider. And also there is a dynamic picture. It's what is happening during the algorithm. And they are just from independent somehow, but we need to prove that some combination of circumstances is not possible. Okay, let's try. It's always difficult to prove, but let's try, see what we can do. The proof is an induction proof, and induction is by rejection moment. So during the algorithm, there are several rejections. So some proposals are rejected, or some pairs are dissolved, and in both cases, some women reject some men, and so this is what has happened with M and W, and so there are a sequence of rejections, and we prove induction by induction over this rejection moment. Okay, so assume that the claim is false and some pair MW appears in a stable matching. But in the contrary to what we the claim, still W was rejected by M. And what does it mean? That there is some when a rejection happens, a woman gets a better candidate. Either it has it from at the moment of rejection, a proposal, or a new proposal comes. But in both cases, there is this red line shows that in the algorithm, woman W was connected to some other better candidate than in our stable thing. Okay, but this better candidate M prime in the stable picture he is also connected to some woman, different one because it's perfect matching, and this woman is W prime. So we have two pairs MW and M prime W prime in the stable matching, and this red line means that during the algorithm there was a pair M prime W. And now we want to use that the matching is stable. And what does it mean? Since by construction M prime was better than M for W, then the only way why this will not be an unstable situation is the viewpoint of M prime. M prime should believe that the stable partner W prime is better than W. So we get we know that this we have some this information about ordering. And recall that during the algorithm, this M prime was paired with W. And so, look, W prime is better for M prime. So why, if finally M prime, not finally, if at some point M prime was paired with W, this means that earlier he tried to be paired with W prime because W prime is earlier in the list. So he was earlier rejected by W prime before all this happens. And we get a contradiction with the induction assumption. We see that now, look, M prime was rejected by W prime. And on the other hand, we assume that they appear in the stable matching. So this is the thing which cannot happen. So this cannot, we see that it happens for M prime and W prime, which is exactly what is forbidden by our claim. So this is the inductive proof. It's a bit strange, but you can carefully check all the steps, and each step is rather simple, but the problem is that they are not very natural. It's difficult to see all of them together in one argument. Anyway, here is the proof. Now we want to show that the algorithm is double unfair. So it's not only treats the men in the most favorable way, it also treats women in the most unfavorable way. So let's explain what does it mean. Again, it's just the same setting. So if we have some woman in different stable matchings, this woman can have different partners. And the algorithm will give one of these partners. And what we claim, that the algorithm will give the worst one. So there are many possibilities, but our algorithm is somehow maximally mean. It will give the worst possibility for every woman. So why it happens? Again, we can try to reformulate it in a more specific way. So imagine we say that we want to say that if MW is in some stable matching, then our algorithm cannot provide something better. So if we take the worst stable matching, our algorithm will provide this partner. So it cannot pair W with some better candidate M. If there is some stable, if in some stable matching W is paired with M. Okay, again we need to rewrite to see it. We start our proof by repeating the claim, and just the same claim. Now let's look what does it mean. So we assume here, this is in the picture, MW appears in some stable matching. So the stable matching is a static picture and it's shown in black. And so here is the connection. And there is dynamic picture. Imagine that the claim is false, which means that our algorithm pairs W with M prime, which is better than M. There is this red thing is what our algorithm gives at the end. And then, of course, this M prime in the stable matching, M prime is also involved. So it's paired with some W prime. Again, again the same reasoning. So we know that for W, M prime is better than M. So why this red line doesn't destroy the stability? The only reason why it can happen is just the opinion of M prime. So for M prime, W prime should be better than W. Otherwise, this black connection is not stable because the red line will make it unstable. Okay, and let's look what happens for M prime. We see that in some stable matching, he is paired with W prime. And our algorithm paired it with W, which is worse than W prime here. W is worse for M prime than W. W prime is better than W for M prime. So we see that the algorithm, the red line, is worse than the stable matching. And we know it's just the first part of our statement that for men, for all men, including M prime, the algorithm should give the best result. So the best result is at least W prime, and now the algorithm gives W, and this is not possible according to our assumption. So the second part is just, we do not make now any induction, we just use the statement we had from the first part. Okay, so we are almost finished. Let me make some general remarks about what is happening. So first, I would say that somehow it's a bit counterintuitive. Why this algorithm favors men over women? Somehow you can say that men are more restricted. They never are allowed to leave their partners by their own will. So the existing pair is broken only if the woman wants this. And the women are allowed to do this. If the woman gets a better proposal than the current partner, then she accepts it. So somehow there is more freedom for women. And still, strangely, the algorithm favors men. But here the man is in quotes, because of course I should repeat again and very strongly what I have said before, that just when we speak about men and women in our discussions, they are not real men and women. They are just some entities, some names for algorithmic entities, and there is no claim or of any similarity between the conclusions about the algorithm and anything about the real life. So there are there are cases when this model is really relevant for this admissions, for donors, for other cases. But the marriage problem is not modeled by this. It's just a way of saying things to make the proofs more easy to remember or easy to understand and so on. So don't take it seriously at any rate. So what if we want to apply this in practice? Then we need to extend the model in different ways. So first, like in admissions and university, it's not one-to-one correspondence, of course. University corresponds to many applicants. So we need to extend the algorithm to this case. Also, sometimes there are no preferences. So there are a group of people which are equally good for some job, or some student doesn't know much about several universities and treat them as essentially of the same level. So there is equality is also possible. And also there are cases when for some candidates some job are completely unacceptable, so or vice versa. So it's better not to have a job at all than to have this job. So this is also not, in our simple case, it was not allowed also. And there is a more subtle thing, which is this is a protocol. The question is whether it's truthful. What does it mean? That imagine that people, for example, students, they send. Imagine they send the list of preferences for university to some central committee, which will process all the data and provide the matching. But of course, they are not interested in sending the truth. They are not obliged to send real preferences. Maybe if they send something wrong, this will force the central committee to the central processing unit provide better outcome for them. So it's a general, any economic mechanism should be asked whether it's truthful or not, whether it's encouraged telling the real preferences, or just whether telling the real preferences is the best strategy. It's a very important economic things, but it's beyond our computer science and discrete mathematics topic. But I just want to say that if you like the setting, if you like this type of questions, you should think about taking some course in mathematical economics. It's a very interesting course, a very interesting topic, and also you see that it's not difficult to get a Nobel Prize for such a simple algorithm. Just kidding. But anyway, economics is really interesting. So if you get a feeling, a bit of feeling what is economics, then you can decide whether you want to study it more seriously, and it's recommended.